Hello, and welcome back into the dark.
Tonight we'll spend some time exploring a creature most of us will never meet. A creature that lives where the light barely reaches. A creature whose name comes from a comparison, not to another insect, not to another animal, but to a bullet.
The bullet ant.
An inch of armored body walking alone beneath the roots of the world's oldest forests. We'll sit with it for a while. We'll listen to the sound it makes before it strikes. We'll learn the chemistry of its venom, the worst pain a human being has ever measured. And we'll meet the people who, for reasons that go back longer than any of us can trace, willingly press their hands into a glove filled with these ants 20 times across a lifetime. 100 facts, 5 stages, one small creature that has outlived more history than we have. Stay close. Keep the lights low. Let's begin. The bullet ant earned its name in the cruelest way possible. The first English speakers to feel its sting did not reach for the language of insects or even of larger animals. They reached for the language of weapons, a gunshot, a round entering the body. That, they said, was the closest comparison their bodies could find, and the name has held for more than a century, because no one who has been stung has ever offered a better one. The scientific community accepts the comparison too, not as folklore but as a useful description of what the nervous system actually experiences. The Schmidt Pain Index, the only formal scale of insect sting pain, places the bullet ant at the very top, above the tarantula hawk, above the warrior wasp, above every honeybee and yellow jacket and fire ant that has ever ruined a backyard barbecue. Justin Schmidt, the entomologist who built that scale by being stung by nearly every stinging insect he could find, described the bullet ant's sting as walking over flaming charcoal with a 3-inch nail embedded in the heel. Imagine standing barefoot on a piece of rebar pulled fresh from a furnace. That is the comparison researchers and victims keep returning to. The strange thing is that the ant itself is not large by mammal standards. It is roughly the length of a quarter coin laid on its side. Yet something about the chemistry of its venom and the precision of the strike creates a sensation human beings have never found another word for. So we call it what it feels like, a bullet. Long before anyone called this creature a bullet ant, scientists gave it a name in Latin, Paraponera clavata. The first half Paraponera means near Ponera, a reference to a related genus of ants known for their primitive features. The second half clavata comes from the Latin word for club, or clubbed, a nod to the shape of the antennae and the sturdy, almost weighted body of the insect. The formal name reads roughly as the club-shaped ant near the old ones. There is something fitting about that, because the bullet ant truly is one of the oldest of its kind. Its lineage stretches back tens of millions of years into a world before grasses, before flowering trees in their modern form, before any human ancestor walked upright. Scientists still debate exactly how far back the line extends. Fossil evidence in amber suggests at least 60 million years, possibly more. The clavata in its name is not just descriptive. It speaks to a body built like a tool, heavy in the right places, compact, functional, designed for survival in a forest that has tested it longer than we have existed. You might think of the name as a kind of fingerprint left behind by the early naturalists who first held one of these ants in their hands. Europeans mostly working through the rainforest with notebooks and butterfly nets trying to find words for what they were seeing. And what they were seeing even then was something ancient, something that had been there long before they arrived. Something that would still be there long after. Most ants are forgettable in size. A speck on the kitchen counter, a flicker across the sidewalk. The bullet ant is not. A full-grown worker measures roughly an inch from mandible to abdomen, about the length of an adult human thumbnail. Lay one across the palm of your hand, and it would stretch from one knuckle line to the next. Set it beside a typical sugar ant from your kitchen, and the bullet ant looks like a wolf standing next to a house cat. This is the largest stinging ant on Earth, and one of the largest ants of any kind. The queens are larger, still closer to an inch and a quarter, and have a presence that early explorers sometimes mistook for a small wasp. Size matters in the world of ants. Most colonies make up for the smallness of their members through sheer numbers, building societies of tens of thousands, sometimes millions of individuals. The bullet ant does not play that game. It walks heavier. It works alone more often than it works with others. Its size lets it hunt prey other ants cannot and carry weight other ants would struggle with. Imagine a single ant capable of dragging a grasshopper twice its own body length across the forest floor. That is the kind of strength that comes with a body this large. And yet there is no swagger in how it moves. The bullet ant walks the way an old soldier walks. Slowly, deliberately, aware of every step, like it knows it doesn't need to hurry. Because nothing else in the forest wants what it carries inside. A bullet ant's body is not the dull brown or black of common ants. It carries a color closer to dried blood, a deep reddish black that catches the dim rainforest light in a way that almost shimmers. The exoskeleton is thicker than most ants too, almost armored with ridges along the thorax and abdomen that look hand-carved. Entomologists have long noted that this is the look of an old design. A body that has been refined over a very, very long time, and then stopped changing because there was no longer any need. The hardness of the cuticle protects the ant from the bites of other insects, from falls inside the canopy, from the abrasive bark of the trees it climbs. Run your finger across the back of a dead specimen and it feels less like an insect and more like a small polished stone. That toughness is part of why early colonial naturalists in South America wrote letters home describing the ant as something between a beetle and a wasp. They had simply never seen an ant built this way before. Scientists still debate whether the armor evolved primarily for physical defense, or for some other reason, perhaps to retain moisture during dry seasons, or to withstand the chemical defenses of certain rainforest plants. What is not debated is what the armor signals. A creature that has lived in roughly the same form on roughly the same trees for tens of millions of years. The bullet ant's body is in a sense a record of how long the rainforest itself has stood. The bullet ant does not live just anywhere. Its range is specific and it is shrinking. Today you can find it from southern Nicaragua through the rainforests of Costa Rica and Panama, down across the entire Amazon basin and as far south as the forests of Paraguay. A stretch of land roughly equivalent to the distance from New York City to Mexico City. All of it draped in the green ceiling of tropical rainforest. The ant does not tolerate dry climates. It does not tolerate cold. It does not tolerate the cleared edges of farmland or the bare ground of cattle pasture. It needs the deep humidity, the constant shade, the soft layer of fallen leaves that only a primary rainforest can offer. Within that range, the population is not evenly spread. The ant prefers older forests with large emergent trees, the giants that punch through the canopy and create the buttress roots where colonies live. In younger regrown forests you can sometimes find them, but the colonies tend to be smaller and farther apart. Anywhere there has been heavy logging within the last century, the bullet ant is often simply absent. You can walk for hours through a damaged forest and find every other kind of ant, fire ants, leaf cutters, army ants, but not a single bullet ant. This makes them in a strange way a quiet witness to the health of the land. Where they remain, the forest is old. Where they have vanished, something has gone wrong. Researchers have begun using their presence or their absence as a kind of natural map of the rainforest that still survives. A bullet ant colony does not announce itself. There is no mound rising from the forest floor. There is no obvious hole. To find a nest, you have to walk to the base of one of the great trees of the rainforest, a kapok, a Brazil nut tree, a strangler fig, and look at the place where the trunk widens into the buttress roots. Those huge flaring walls of wood that hold the tree upright in shallow tropical soil. The bullet ants build between them. Inside, the dark, humid spaces where root meets earth, they carve out chambers in the soft soil and decaying wood. A typical nest extends a few feet down and several feet across, with multiple openings disguised by leaf litter and moss. You could stand inches from a colony of 1,000 bullet ants and never know they were there. They like it that way. The choice of host tree is not random. Bullet ants tend to favor certain species trees with stable buttresses, with bark that resists rot, with branches that produce nectar near the ground. There is often a quiet exchange between ant and tree. The ants protect the tree from herbivores by attacking anything that tries to climb it. The tree in turn provides shelter and sometimes food. If you have ever stood in an old-growth forest and felt the unmistakable sense that the place was alive, that something was watching you from the dark beneath the roots, there is a real possibility you were right. The bullet ant lives in that exact silence. It hunts there, it listens there, and it almost never lets itself be seen. The mandibles of a bullet ant look almost cartoonish on a creature this size. They curve inward like a pair of black sickles, meeting at the tips in a sharp scissoring point. Each mandible is operated by a powerful muscle that fills much of the head. The reason a bullet ant's head looks disproportionately large compared to most other ants. The bite is strong enough to crush the shell of a small beetle, sever the leg of a katydid, or carry a piece of fruit weighing several times the ant's own body weight. To picture the strength involved, imagine a human being lifting a refrigerator above their head using only their teeth. That ratio is roughly what a bullet ant pulls off when it carries a large prey item back to the nest. The mandibles are not the primary weapon, however. That role belongs to the stinger at the rear of the abdomen. The mandibles are for work, for grip, for dragging food across roots and bark and damp leaves. They are also for combat when a colony comes under attack from army ants or raiding columns of other species. A bullet ant in defense mode bites first and stings second. The bite alone is painful, a sharp, deep pinch that draws blood from human skin without much effort. But the sting is what people remember. The bite is just how the bullet ant holds you still long enough to do what comes next. Researchers studying ant evolution have noted that the bullet ant's mandible structure has remained largely unchanged across millions of years. It is in essence the same set of tools the species was using when our earliest mammal ancestors were still hiding from dinosaurs. There is a sound a bullet ant makes that most people do not associate with ants at all. It is a soft, high-pitched chirp, almost like a tiny cricket. The ant produces it by rubbing a ridged section of its abdomen against a small file-like surface on the thorax. The process is called stridulation, the same mechanism that crickets and grasshoppers use to make their songs. In bullet ants, it is not a song. It is a warning. When a bullet ant feels threatened, disturbed in its nest, picked up, stepped near, it chirps. The sound is barely audible to a human ear at more than a few feet away. But up close with your ear near the leaf litter, it is unmistakable. A small, sharp, almost musical note in the dark. Researchers believe the stridulation serves at least two purposes. The first is communication with other ants in the colony, a kind of alarm call that signals danger. The second is a warning to whatever predator has come too close, a reminder that the next thing this small body produces will not be a sound, it will be a sting. There is something almost polite about it, in a way that feels strange to say about an insect. The bullet ant does not strike first. It announces itself. It tells you in the only language it has to back away. Most creatures of the rainforest understand the message. The ones that ignore it, coatis monkeys, occasionally birds, usually do not make the same mistake twice. For human beings unlucky enough to be in the wrong place, that chirp has become known to local guides as the last warning before the worst pain of your life. In the rainforest, there are creatures you see before you hear, and creatures you hear before you see. The bullet ant belongs firmly to the second category. Walk along a forest trail in Costa Rica or Peru at dusk, and you may catch a faint repeating chirp, high and thin, just above the layer of frog calls and night insects. Look down. The source is almost certainly somewhere near your boots. Local guides who lead tourists through these forests will often stop suddenly at the sound. They do not panic. They do not move quickly. They simply hold up one hand and listen the way a tracker might listen for a rattlesnake, because the chirp tells them with precision where the ant is. From there, they know exactly where not to step. This is part of why the bullet ant has become such a feared presence in the forests where it lives. It is not aggressive in the way of fire ants or army ants. It does not swarm. It does not chase. But it does not run from you either. It holds its ground, makes its sound, and trusts the rest of the forest to know what that sound means. For human visitors, the rule is simple. If you hear that chirp, you stop. You back up. You let the small armored creature on the leaf go about its business. The forest has a kind of etiquette written in sounds rather than words, and one of the oldest rules of all is the one written by the bullet ant. When it speaks, you listen. When you listen, you live. Watch a sugar ant on a kitchen counter and you see chaos in motion. Quick darting steps, sudden reversals, a frantic checking of the air with the antennae as if the ant has forgotten where it left its keys. Watch a bullet ant on a rainforest trunk and you see something completely different. The bullet ant moves slowly. It places each leg with care. It pauses often to test the air or the surface with its antennae. There is no panic in its motion. There is no rush. To anyone used to the speed of common ants, the first sight of a bullet ant walking is almost surreal. It looks in some lights less like an insect and more like a small, deliberate animal, a miniature predator on patrol. Entomologists have offered several explanations for this gait. The size of the ant is one factor. Larger insects often move more slowly because their bodies require more energy to accelerate. The solitary nature of its foraging is another. A bullet ant that has wandered off alone cannot afford a misstep. There is no swarm of nestmates coming to its rescue. Every movement must count. And then there is the simple fact that a bullet ant has very few predators to fear. Its sting is so well known among the larger animals of the rainforest that almost nothing will challenge it. When you carry the worst sting in the world, you do not have to run. Imagine a heavyweight boxer crossing an empty ring. Slow steps, weight balanced, no wasted motion. That is roughly how a bullet ant carries itself through the forest. Quiet, unhurried, aware that whatever it meets, it will almost certainly walk away from the encounter. If you spend long enough watching a bullet ant, you start to notice the antennae. They never stop moving. They sweep the air ahead of the body, tap the surface beneath the feet, brush against passing leaves, and sometimes when the ant pauses, they fold gently back along the head as if listening. Those antennae are doing far more than feeling around in the dark. They are reading the forest the way you might read a paragraph of dense foreign text. Each segment is lined with tiny sensory hairs, hundreds of them per ant, each one tuned to a specific kind of chemical signal. The bullet ant uses them to detect pheromone trails, to identify nestmates from intruders, to track prey by scent, and to sense the breath of an approaching predator long before it appears. To get a sense of what this means, imagine if your hands were also your eyes and your ears at the same time. That is roughly the role the antennae play. The world arrives through them as a constant stream of information, layered and overlapping in a language built entirely of chemistry. Scientists are still working out exactly how much detail a bullet ant can perceive through its antennae. Some studies suggest they can identify individual members of their colony by chemical signature alone, a kind of olfactory face recognition. Others suggest they can detect microscopic differences in the bark of different host trees. In a forest where vision is limited by darkness and dense vegetation, the antennae are the bullet ant's primary tool for understanding what is around it. Without them, the ant would not just be blind, it would be lost in a language it could no longer read. There is a certain image that anyone who has worked in the Amazon eventually carries with them. A single bullet ant alone, standing motionless on the upper surface of a broad green leaf. The light coming through the canopy catches the dark armor of its body. The antennae move slowly, almost gracefully. The ant is not hurrying. It is not searching. It is simply there, and there is something about the sight that is difficult to describe to anyone who has not seen it. The closest word might be dignity. Most insects look small and frantic and concerned with the next inch of ground. The bullet ant alone on its leaf looks like something else, like a small patient animal that has stopped to consider where it is. Naturalists who have spent decades in the rainforest sometimes write about this moment with a strange tenderness. There is a sense when you see it that you are watching a creature that does not need anything from you, that has no fear of you, that is in its own quiet way the ruler of the small piece of forest it occupies. If you have ever stood very still in the woods and felt just for a moment that the place around you was holding its breath, you have felt something close to what a bullet ant lives inside every day. Researchers who try to study bullet ants in the wild often describe the difficulty of approach. The ant does not flee, but it does not invite you in either. It simply waits, watches, and after a while walks on, like a small armored ghost of a forest much older than ours. Inside every bullet ant colony lives a single individual unlike any of the others. She is larger than the workers, sometimes by a noticeable margin, with a heavier abdomen designed to carry the developing eggs that keep the colony alive. Her movements are slower still than those of her daughters outside, partly because she rarely leaves the safety of the nest, and partly because her role does not require speed. Her role requires endurance. A bullet ant queen can live for years, sometimes for more than a decade in the wild, an extraordinary lifespan for an insect of her size. Compared to a typical honeybee queen, which may live 3 or 4 years, the bullet ant queen is a near immortal figure inside her colony. Some researchers have estimated from long-term observation that certain bullet ant queens may approach 20 years under ideal conditions, though scientists still debate just how long is truly possible. The colony depends on her completely. If she dies, no other ant in the nest can take her place. The colony will continue to function for a time, defending the nest and gathering food. But new workers will stop being produced. Slowly the population will dwindle. Within a few years, the last of the workers will die. The colony will simply end. There is something almost royal about her existence, though royalty here means responsibility, not luxury. She lays the eggs. She is fed by her own daughters. She rarely sees the sun. She is the still, slow center of everything the colony does. And when she is gone, the small empire built around her quietly fades into the forest floor. A bullet ant worker is built to last. Unlike the short-lived workers of many ant species, which may live only a few weeks before dying of exhaustion, a bullet ant worker can live for over a year, sometimes closer to 2. That is a remarkable stretch of time for an insect that spends most of its life walking, climbing, and occasionally fighting other large insects in the rainforest understory. It is the kind of lifespan that allows a single bullet ant to develop something close to experience. Worker bullet ants are not interchangeable units in a swarm. They learn the territory around the colony, memorize foraging routes, remember the locations of nectar-bearing trees, and recognize the chemical signatures of their nestmates. Older workers are believed to take on slightly different roles than younger ones, guarding the nest, leading foraging trips, defending against intruders. The colony, in other words, is not a uniform mass. It is a community of individuals with histories. Researchers studying bullet ant workers have noticed that the oldest individuals tend to be the most cautious. They sting less often. They retreat more readily. They have, in some sense, learned the cost of confrontation. Younger workers, by contrast, are more likely to attack first and chirp later. It is one of the small, quiet surprises of studying these animals, that an insect given enough time can build up something that almost resembles wisdom, not because anyone taught them, not because the colony rewards it, but because the rainforest, when you live in it long enough, tends to teach the same lessons it has been teaching every creature that walks under its trees for the last 50 million years. Bullet ants are climbers as much as they are walkers. A typical foraging trip takes a worker not just across the forest floor, but high up into the trunks and lower branches of the rainforest canopy. They travel up the bark of trees that would defeat almost any other ant their size, gripping the rough surface with hooked claws and small adhesive pads on their feet. To picture the kind of climb this represents, imagine a human being scaling a redwood tree, the height of a skyscraper, using only their hands and the calluses on their fingers in the dark in the rain. That is what a bullet ant pulls off on a regular night of foraging. The ant's body is well suited to the task. Its center of gravity is low. Its legs are long and well muscled. Its claws can grip into the smallest imperfections in bark, and the fine hairs along its feet seem to provide additional traction on slick or wet surfaces. Researchers studying the climbing ability of bullet ants have noted that the ant rarely slips, even on bark made slick by rainfall. When it does lose its footing, the body is small enough and tough enough that a fall is almost never fatal. The ant simply lands, gathers itself, and begins climbing again. The forest is for the bullet ant a vertical world as much as a horizontal one. The nest sits low in the buttress roots, but the food often lives in the canopy. Every night, a steady, silent traffic of bullet ants moves up and down the trunks of the great trees, invisible to most of the creatures around them, doing the slow, patient work of a hunter that knows the territory by heart. The eyes of a bullet ant are large compared to those of most other ants. 2 dark, slightly bulging compound eyes set on either side of the head. Each eye is made up of hundreds of tiny lenses called ommatidia, each one capturing a narrow slice of the visual field. Stitched together, those slices create a kind of mosaic image of the world. It is nothing like what you see when you look into the forest. A bullet ant's vision is in some ways blurrier than a human's. The resolution of a compound eye, even one as well developed as theirs, falls short of a vertebrate's eye in fine detail. But in other ways, the bullet ant sees things you never will. Compound eyes are excellent at detecting motion. A bullet ant can pick up the smallest movement at the edge of its field of view from many inches away. Compound eyes are also sensitive to certain wavelengths of light, particularly into the ultraviolet range. To a bullet ant, the colors of flowers and leaves may glow in patterns invisible to us. Imagine watching the rainforest through a screen made of hundreds of tiny windows, each one tuned slightly differently. That is closer to how its sight is built. Scientists are still working to understand exactly how much detail a bullet ant can perceive, especially at night when the ant is most active. Some researchers believe the eyes function more as motion detectors in the dark, with the antennae doing most of the navigation. What is clear is that the bullet ant does not need clear sight to be an effective hunter. The forest gives it everything else: sound, scent, vibration, touch. The eyes are only one window. The rest of the body is open. The body of a bullet ant is covered in a fine layer of microscopic hairs. Under a microscope, though, they form a dense forest of sensory bristles, each one connected to nerves that feed information directly to the ant's brain. These hairs can detect air movement, vibration, humidity, and even subtle shifts in barometric pressure. There is good evidence that bullet ants can sense an approaching rainstorm before any clouds have darkened the sky. Long before the first drop falls, the colony begins to change its behavior. Foragers return to the nest. Entrance tunnels are partially blocked with leaf litter. The ants gather in deeper chambers. By the time the rain actually arrives, the colony is already prepared. To imagine what this kind of sensitivity feels like, picture the way the hair on your forearms stands up just before a thunderstorm. That small electric awareness in the body, the moment when something has changed in the air and you cannot yet name what. The bullet ant lives inside that feeling, but on a scale orders of magnitude finer. It is not just sensing the storm. It is reading the air the way you might read a weather report. Researchers studying these sensory hairs have noted that they also help the ant detect the movement of nearby predators, the wing beats of approaching insects, and the footfalls of larger animals. In the dense, dark world of the rainforest understory, this kind of sensitivity is essential. Vision can only do so much. Smell only carries so far. The forest to a bullet ant is something you can feel before you can see. Long before any biologist labeled the bullet ant with a Latin name, the people who lived alongside it had names of their own, stories of their own. In the languages of the Amazon, the bullet ant goes by many names: Tocandida, Hormiga 24, Isula, Conga. Each name carries a kind of warning, and sometimes a kind of reverence. In several indigenous traditions, the bullet ant is more than just a dangerous insect. It is treated as a being with spirit, with intention, sometimes even with judgment. There are accounts gathered by anthropologists in which elders speak of the ant as a guardian of the forest, a small, silent watchman that punishes those who walk through the trees with disrespect. In other traditions, the ant is associated with strength, with endurance, with the kind of patience that allows a creature to survive long after stronger things have died. Scientists and anthropologists still debate how much of this folklore reflects direct observation of the ant's behavior and how much reflects something deeper, a relationship between forest peoples and forest creatures that runs back thousands of years. What is clear is that the bullet ant has not been in these traditions simply an insect to be avoided. It has been something to be acknowledged, something whose presence carries meaning. The chirp before the sting is not just noise. It is a small declaration, a statement made by something old in a forest older still. The bullet ant does not just bite, it speaks, and the forest in its way has been listening to it for a very long time. Ask any biologist what defines an ant colony, and the first word that comes back is almost always cooperation. Ants forage in trails. Ants follow chemical paths laid down by their nestmates. Ants share food, share work, share danger. They are the textbook example of a swarm intelligence where the colony as a whole is the real organism, and the individual ant is just a moving cell in that larger body. The bullet ant breaks this rule. A bullet ant leaves the nest alone. It walks out into the forest alone. It hunts alone. It carries food back alone. There are no long, glistening trails of bullet ants threading through the leaf litter. There is no army on the march. There is just one ant on its own, doing its work in the dark. To find another example of this kind of behavior in the ant world, you have to look hard. A handful of bullet ant relatives forage solo, but among the roughly 12,000 known species of ants, true solitary foraging is rare. Almost a contradiction in terms. Imagine a hive of bees where each worker left alone, gathered pollen alone, and flew home alone, never sharing the location of a single flower with anyone else. That is roughly what bullet ant foraging looks like. Scientists still debate exactly why this behavior evolved. Some believe the size and ferocity of bullet ants make them capable predators on their own with no need for the safety of numbers. Others suspect the solitary habit may be related to a diet of widely scattered nectar sources and prey items too small to require group hunting. Whatever the reason, the bullet ant walks alone, and in a world built on the cooperation of insects, that alone makes it strange. A bullet ant colony is unusually small, where a leafcutter colony might house several million ants, and a fire ant mound can hold over 200,000. A bullet ant nest typically contains only a few hundred individuals, sometimes fewer than 100. In rare cases, a mature colony may reach 1,000, but rarely more than that. To put that in perspective, a single bullet ant nest is about the size in population of a small American high school. Not a city, not a town, not a sprawling empire, a community, small enough that it would not be unreasonable to imagine every worker knows, at least by chemical signature, every other worker in the nest. This small population shapes everything about how the colony behaves. There is no surplus of workers to throw at problems. Every individual matters. The loss of even a handful of foragers to predators or accidents can have a measurable effect on the colony's food supply. Defense relies not on overwhelming numbers, but on the disproportionate violence of each individual sting. Researchers who study colony size across ant species have noted that bullet ants sit at one extreme of a long spectrum. On the other end are species like the driver ants of Africa, whose colonies can swell into the tens of millions. The bullet ant has chosen, evolutionarily speaking, almost the opposite strategy: quality over quantity, force over volume. And in the strange logic of the rainforest, it works. The forest is full of ants in vast numbers, but almost none of them are as feared or as carefully avoided as the small colony of a few hundred living quietly beneath the roots of a single great tree. Standard ant nests come in familiar shapes: the dome-shaped mound of a fire ant colony, the underground city of a harvester ant, the leaf tent of a weaver ant. The bullet ant builds something stranger than all of them: a nest carved directly into the body of a living tree. When a colony settles into the base of a rainforest giant, it does not just take up residence between the roots. It excavates. Workers chew through soft, rotted wood. They carry away grains of damp soil, one mandible load at a time. Over months and years, they hollow out a network of chambers and tunnels that wind through the buttress and into the earth beneath. Some chambers are used for raising brood, the eggs, larvae, and pupae that will become the next generation of workers. Some are used for storage. Some are kept empty as escape routes or refuges during heavy rain. A mature bullet ant nest can have dozens of chambers connected by narrow tunnels. From the outside, you might see only one or two openings, often hidden under leaf litter. From the inside, it is a small underground city built into a structure that is itself still growing. The host tree, in most cases, is not harmed by this construction. The ants work mostly through wood that has already begun to decay and through the soil between the roots. The tree continues to grow above them. The ants live below in the dark, in the damp, in the slow heartbeat of the rainforest floor. Imagine a house carved into the foundation of a redwood. That is, in miniature, what a bullet ant colony has done. The structure of a bullet ant colony does not look like a corporation. It does not look like an army. It does not even look like a typical insect society. It looks more like a small medieval court with the queen at the center and her daughters arranged in concentric rings of attention around her. The queen rarely moves. She sits in the innermost chamber of the nest, usually one of the deepest and most protected. Around her, a small group of attendants tends to her constantly. They groom her body, removing fungal spores and parasites. They feed her droplets of nectar and pieces of prey brought back from the forest. They carry away the eggs she lays one by one and place them in the brood chambers where they will be cared for by other workers. Beyond that inner circle is another layer of workers, those tending the developing brood. Beyond that, the workers who maintain the nest repair tunnels and stand guard at the entrances. Beyond all of them, out in the forest, the solitary foragers who walk into the dark every night. There is no other ant in the world quite like a bullet ant queen. Not in her size, not in her lifespan, not in the strange, slow patience with which she presides over a colony that depends entirely on her existence. Scientists studying bullet ant social structure are still trying to map the precise roles of different workers around the queen. The colony, despite its small size, appears to have a more intricate inner order than was once believed. It is not a swarm. It is a kingdom, a quiet one, carved into the roots of a tree. Most ants communicate with their nestmates through a vast and detailed pheromone language. Trail pheromones to mark food routes, alarm pheromones to call workers to defense, recognition pheromones to identify friend from foe. The chemical conversation inside a typical ant colony is constant, layered, and loud. The bullet ant speaks a quieter version of this language. Because workers forage alone, there is no need for the elaborate trail marking system that defines most ant societies. A bullet ant does not lay a chemical path through the forest for others to follow. It walks alone. It returns alone. The route exists only in its own memory. Inside the nest, however, the language is still used. Workers identify one another through chemical signatures on their bodies. Alarm pheromones are released when the colony is under attack. The queen produces specific chemicals that signal her presence and her health to those around her. When she begins to weaken, the chemistry of the nest changes and the workers can sense it. Researchers have noted that the bullet ant's pheromone vocabulary, while less developed than that of many other ant species, includes some unique compounds not found elsewhere. Scientists still debate exactly what each of these chemicals means. Imagine walking into a room where everyone already knows who you are, where no one needs to call out your name because your presence has already announced itself before you step through the door. That is closer to how bullet ants talk to one another. The forest is a noisy place. The bullet ant has learned to speak softly inside it. The relationship between a bullet ant colony and its host tree is older than almost any partnership in human history. It is a kind of mutual contract written entirely in biology and never in words. The bullet ant chooses certain trees over others. Cecropia, Brazil nut, kapok, strangler fig, trees with stable buttresses, generous nectar production, and a tendency to host other small creatures the ants can hunt. The ant gets shelter food and a vertical highway into the canopy. The tree in return gets one of the most fearsome bodyguards in the entire forest. Anything that tries to climb the trunk of a bullet ant tree, herbivorous insects, leaf-eating beetles, even some small mammals, runs the risk of meeting a worker. Or not leaving at all. Studies in Central America have shown that trees hosting bullet ant colonies suffer significantly less leaf damage than nearby trees of the same species without such a colony. To picture the kind of arrangement this represents, imagine a homeowner who hires not a security system but a small private army. An army that lives in the basement, asks for nothing more than a few drops of sugar water, and patrols the perimeter every single night. It is not a perfect partnership. The ants do not protect the tree consciously. They simply live there, defend their territory, and the tree benefits as a side effect. But the result over millions of years has been a quiet coevolution. Certain trees produce nectar specifically at the heights where bullet ants travel. Certain bullet ants prefer certain trees almost exclusively. They have grown up together, and they still keep each other alive. For an insect with such a terrifying reputation, the bullet ant has a surprisingly sweet tooth. A large portion of its diet, by some estimates, the majority consists of nectar gathered from the canopy of the rainforest. Many tropical trees produce extrafloral nectaries, small glands on leaves, stems, and branches that secrete droplets of sugary fluid even when the tree is not flowering. These nectaries exist in many cases precisely to attract ants, like the bullet ant, drawing them up into the canopy where they can serve by accident as guards against herbivores. A foraging bullet ant will spend much of the night climbing through the branches, drinking from these tiny wells of sweetness. The sugar fuels its long climbs, its slow patrols, its strength. There is something almost gentle about the image. An insect feared above all others, sipping quietly from a leaf in the dark. If you have ever wondered why something built for combat would spend so much of its life drinking sugar water, the answer is simple: energy. A predator the size of a bullet ant needs an enormous amount of fuel to move, climb, hunt, and sting. Nectar provides it cheaply and abundantly. It is the gasoline that powers the rest of the engine. The protein, the substance the colony actually needs for growth and brood development, comes from elsewhere. From the prey the worker eventually hunts. But the daily walking, the slow nightly patrols, the constant climbing, all of it is powered by sugar, pulled from leaves the size of dinner plates in trees taller than most office buildings. The bullet ant, for all its menace, runs on the sweetest thing the forest has to offer. The other half of a bullet ant's diet is anything but sweet. When a worker is hunting for protein, it becomes one of the most formidable solitary predators its size in the rainforest. The targets are usually other insects: beetles, katydids, caterpillars, spiders sometimes, smaller ants occasionally. The bullet ant is opportunistic. If it moves, and it is not too large to overpower, it is potentially food. The hunt is patient. A bullet ant does not chase. It stalks. It moves slowly across a leaf or a piece of bark antennae, sweeping until it senses something nearby. Then it freezes. Then it advances. When it strikes with both mandibles and stinger at the same moment. The mandibles grip the prey. The stinger drives into the body. The venom, designed to overwhelm the nervous system of an animal far larger than a beetle, kills small prey almost instantly. To imagine the violence involved at scale, picture a creature the size of a house cat hunting and killing a deer with a single bite. That is roughly the predatory ratio a bullet ant achieves on its larger prey. Once the prey is dead, the work begins. The bullet ant must drag, carry, or partly dismember the kill in order to bring it back to the nest. A single katydid might take a worker over an hour to transport across the forest floor. The journey is dangerous. Other predators are watching. Rain can wash a worker off course. Another colony's territory may lie between the ant and home. But the worker brings it back. Almost always. The colony needs the protein, the brood needs to be fed, and the bullet ant, in its slow, armored way, has just delivered. The bullet ant is at heart a creature of the night. While most of the diurnal insects of the rainforest are settling into hidden places at dusk, the bullet ant is just beginning its working day. Foragers leave the nest as the light fades. They climb into the canopy under the cover of darkness. They hunt, drink, and patrol until something close to dawn, then return to the nest as the first daylight begins to filter through the leaves. There are good reasons for this schedule. Many of the bullet ant's potential predators, birds, monkeys, some lizards, are active during the day. By foraging at night, the ant avoids them almost entirely. The cooler temperatures of the rainforest night also reduce water loss through the ant's exoskeleton, which matters more than you might think for an insect spending many hours away from the moist safety of the nest. The nocturnal habit also matches the activity of the ant's prey. Many of the insects bullet ants hunt are themselves nocturnal, drawn out by the cooler air and the night-blooming flowers. The bullet ant has, in a sense, slotted itself into the rhythm of the rainforest at the time when most of the action happens out of sight. For human beings, this means that bullet ant encounters are far more common at dusk and at night than during the day. Rainforest researchers walking trails after sundown with headlamps will sometimes see in the small pool of their light a single bullet ant on a tree trunk, antennae waving slowly. It is an unforgettable sight. A small, armored shape in the dark, unhurried, almost ceremonial. The forest belongs to many things at night. The bullet ant is one of the slowest and one of the most respected. Bullet ants are remarkably strong, even by the standards of the insect world. A single worker can routinely carry prey items several times its own body weight, sometimes more than 10 times. A katydid, a small lizard, a piece of fruit pulp, all transportable by a single ant working alone. To translate this into human terms, it would be the equivalent of a person carrying a small car on their back across uneven ground in the dark for hours. And doing it more than once a week, the bullet ant manages with no apparent strain. Its body is built for it. Its mandibles grip. Its legs push. Its center of gravity stays low. It walks. There is no team to help. There is no relay system as you might see in leafcutter ants, where workers pass leaves down a long line back to the colony. The bullet ant carries the prey itself from the place of the kill to the entrance of the nest, however far that turns out to be. Sometimes the prey is too large to fit through the opening. In those cases, the worker pauses outside, dismembers the carcass into smaller pieces, and carries them in one at a time. Patient, methodical work performed under the bare beam of moonlight, filtering through the canopy. Researchers studying bullet ant foraging have noted that the largest prey items can take an hour or longer to transport. The worker rarely gives up. Even if it loses its grip and drops the prey, it returns to it, gathers it again, and continues. The colony is waiting. The work has to be done. A small, dark animal carrying a great weight across the floor of the forest. That is one of the truest images of the bullet ant. Most well-studied ant species have complex caste systems, major workers and minor workers, soldiers with oversized mandibles, special foragers, special nurses, special guards. In some species, the differences between castes are so extreme that members of the same colony look like different species entirely. The bullet ant has almost none of this. Inside a bullet ant nest, there is the queen and there are workers. Almost everyone in the colony outside of the queen and the developing brood looks essentially the same. Same size, same shape, same armored body. There are no oversized soldiers. There are no specialized nest builders. There are no tiny nurse castes. The roles are flexible. A worker may spend part of her life guarding the nest entrance, part of her life tending the brood, part of her life foraging in the canopy. As she ages, her role tends to shift outward from inside duties to outside duties, but every worker is capable of doing every job. It is one of the more elegant arrangements in the ant world. A colony built not on rigid specialization, but on individuals capable of adapting to whatever the colony needs at the time. Scientists still debate why this stripped-down caste system evolved in bullet ants. Some believe the small colony size makes specialization unnecessary. There are simply too few individuals to support multiple distinct castes. Others believe the solitary foraging habit reduces the value of specialized workers, since most of the colony's hardest work is done by lone individuals in the forest. Whatever the reason, the result is a colony where every worker is, in essence, every kind of worker, a jack of all trades in a black armored body. The chirp made by stridulation is more than a warning to predators. Inside the colony, it also serves as a communication tool between workers in moments when chemical signals are not enough. A worker trapped under a fallen leaf or buried in collapsed soil after a heavy rain will often chirp continuously. The sound carries through the substrate of the nest, through wood, soil, and root far better than it does through open air. Other workers respond. They follow the vibration to its source. They dig. They lift. They free the trapped sister, and then the chirping stops. In moments of attack, the chirping spreads through the nest like a soft alarm bell. Workers near the entrance who detect a predator begin to chirp. The vibration travels deeper into the colony. Workers in the inner chambers feel it through their feet and through the walls of the nest itself. They emerge ready to defend. To picture this kind of communication, imagine a building with no windows and no electricity, where every wall and floor vibrates softly when someone is in trouble, where the people inside can navigate to one another simply by feeling the building hum. That is, in essence, how the bullet ant uses sound. Not for music, not for territory, not for courtship, for coordination in a world too dark for most other forms of communication. Researchers studying ant stridulation across many species have suggested that sound-based signaling may be more common and more important than was once believed. In bullet ants, where chemical communication is less developed than in most ant species, the vibratory channel may be doing more of the work that pheromones do elsewhere. The colony in the dark listens to itself. When army ants come, they come like a storm, a column of hundreds of thousands of small, dark workers sweeping across the rainforest floor, devouring every insect, lizard, and small animal in their path. For most ant colonies, an army ant raid is the worst thing that can happen. Entire nests are wiped out in hours, the queen carried away, the brood eaten alive. The bullet ant almost uniquely does not lose this fight. When army ants approach a bullet ant colony, the response is not panic. It is preparation. Guards at the nest entrance begin to chirp. The vibration spreads through the nest. Workers from inner chambers move toward the openings. Some block the tunnels with their own bodies. Others gather in defensive clusters, mandibles forward, stingers ready. The arriving army ants, despite their numbers, do not have the size, strength, or chemical weaponry to overpower a bullet ant. A single bullet ant can kill dozens of army ants before being overwhelmed. Most are not overwhelmed. The army column, finding the resistance harder than expected, usually flows around the bullet ant nest and continues on its way. To picture the encounter, imagine a small fortress guarded by a few hundred heavily armored knights, while a horde of much smaller, lightly armed raiders washes against the walls and then retreats. The fortress holds, the raiders pass. It is one of the reasons bullet ant colonies can survive so long in places where every other ant nest is eventually wiped out. They are too dangerous to be worth the cost of attacking. The army ants themselves, among the most feared insects in the rainforest, usually keep their distance. The bullet ant, in its own quiet way, has earned its peace. Inside a bullet ant nest, food is not simply eaten, it is shared. Workers returning from foraging often pass droplets of nectar or partially digested food directly from their mouths into the mouths of other workers. The behavior is called trophallaxis, and it exists in many social insects, but in bullet ants it serves an additional purpose. Because workers forage alone, no two bullet ants experience the forest the same way. One ant might find a particularly rich nectar source on a Brazil nut tree. Another might find a patch of beetles on a fallen log. Trophallaxis lets these solitary discoveries become shared property. Through the exchange of food, the colony's diet stays balanced, even though each individual worker is hunting on her own. There is also a chemical conversation happening during these exchanges. Saliva and digestive fluids carry information about the worker's health, her diet, even her status within the colony. Researchers studying trophallaxis in ants have found that the substances exchanged can include hormones, antimicrobial compounds, and signaling molecules that help the colony function as a coordinated whole. It is, in a sense, the most intimate communication an ant can have. Mouth to mouth, worker to worker, the colony quite literally sharing itself drop by drop in the dark. If you have ever shared a meal with someone and felt closer to them afterward, that small, ancient sense of connection that comes from eating from the same pot you have, felt a version of what trophallaxis does inside a bullet ant nest. The food binds the colony together. The chemistry passes through the same channel as nourishment. A bullet ant is never quite alone, even when it walks alone. The taste of the colony is on its tongue. A bullet ant queen does not produce eggs the way a honeybee queen does. There is no daily flood of new offspring, no relentless conveyor belt of brood. A bullet ant queen lays her eggs slowly, steadily, over years and decades. The colony grows in slow motion, adding a few workers at a time rather than doubling its population in a season. This pace is partly a function of the colony's small size. With only a few hundred workers to feed, raise, and defend, the queen does not need to lay vast numbers of eggs. It is partly a function of her long lifespan. There is no rush. The queen has time. Each egg she lays is small, soft, and pale. It is carried by attendant workers to a brood chamber, where it will be tended carefully until it hatches into a larva. The larva grows over weeks, fed mouth to mouth by the workers, until it pupates and transforms into an adult. The full process from egg to working ant can take many weeks, sometimes months, depending on the temperature and food availability of the season. Scientists studying bullet ant reproduction have noted that the queen's egg production is finely tuned to the colony's needs. When workers are lost to predators or accidents, she lays more eggs. When the colony is at its full strength, she lays fewer. The chemistry of the nest tells her what is needed, and she responds accordingly. It is a slower, more deliberate kind of reproduction than what most ants practice. Less of a factory, more of a workshop, a queen patiently building one ant at a time, the small kingdom that will outlive most of the trees around her. For a new bullet ant colony to exist, a great deal has to go right. A new queen must be produced. She must leave her birth colony. She must mate. She must find a suitable location for a new nest. She must survive long enough to lay her first eggs and raise her first workers, and she must do all of this almost entirely on her own. The process begins with the rare production of winged reproductive ants. Most bullet ants in a colony are wingless workers, but at certain times of year, the queen lays eggs that develop into winged males and new queens. These reproductives leave the colony on a nuptial flight, mating with reproductives from other colonies, before the surviving new queens shed their wings and search for a place to start their own nest. Most do not survive. The new queen is exposed alone and edible to almost every predator in the forest. Birds, lizards, larger insects, even other bullet ants from different colonies, all can end the dream of a new colony before it begins. Of the many new queens produced each year, only a small fraction successfully establish a colony of their own. The ones who succeed dig a small chamber in the soil at the base of a likely tree, often using their own jaws to carve out the first space. They lay their first batch of eggs and tend the larvae themselves, foraging cautiously for food. If they live long enough for those first workers to mature, the workers take over the foraging. The queen retreats inward deeper into the chamber and never leaves again. A single colony is in a sense the rare success at the end of a long lottery. A bullet ant colony, once established, can live for an extraordinarily long time. Estimates from long-term studies suggest that a healthy colony can persist for 15 to 20 years, sometimes more, before the queen finally dies and the colony begins to fade. That is a duration measured not in seasons or in years, but in human chapters. To put it another way, a bullet ant colony living in a tree today may have been there when a child born in the same forest learned to walk, learned to fish, grew up and left for the city. The same colony in the same set of roots beneath the same tree. There is something humbling about this. We tend to think of ant colonies as short-lived things. Flashes of activity in a summer lawn gone by autumn. A bullet ant colony is closer in character to a slow-growing tree itself, a presence in the forest that quietly persists across long stretches of time. This kind of stability has consequences for the surrounding ecosystem. Over decades, a single colony will hunt thousands of prey items, drink from hundreds of nectar wells, and protect the tree it lives in from countless herbivores. The forest is shaped in small ways by the long, patient work of these long-lived colonies. When the queen finally dies, the colony does not end suddenly. It simply stops producing new workers. The aging workers continue to forage, to defend, to tend the empty brood chambers. One by one they die. The nest grows quieter. The chambers grow empty. Eventually the forest reclaims the space, and in the space left behind, another life, sometimes another queen, begins. A bullet ant colony does not function like a city. It does not function like an empire. The closest human analogy might be a small forest tribe, a few hundred individuals living quietly in a single location, drawing food from the surrounding land, raising the next generation, defending themselves when necessary, and otherwise keeping to themselves. The comparison is imperfect. Ants are not people. They do not have language, culture, or memory in the human sense. But the scale of a bullet ant colony and the way it operates within the forest has a tribal quality that other ant societies lack. There is no expansion drive. The colony does not send raiding parties to conquer new territory. It does not split itself into satellites. It does not flood the surrounding forest with reproductive ants in an attempt to dominate the landscape. It simply lives where it lives, hunts what it can hunt, and waits out whatever weather or hardship the forest sends. Researchers comparing ant societies across the world have noted that this kind of low-key, stable, small-scale existence is unusual. Most ant species are expansionist by nature, built to spread, to multiply, to take over. The bullet ant does not seem to be playing that game. Scientists still debate whether this restraint is the result of biological limits, environmental pressure, or some deeper feature of bullet ant social structure. The colony may simply be unable to grow larger because of how much food a few hundred solitary foragers can supply. Or the species may have settled evolutionarily on a strategy of staying small and dangerous. Whatever the reason, the result is a kind of insect society we rarely see. Not a swarm, a small community in the dark getting on with its own quiet business. Despite carrying the most painful sting in the world, the bullet ant is by reputation among those who study it a fairly calm insect. It does not chase. It does not swarm. Most encounters between humans and bullet ants end peacefully because the ant has no particular interest in attacking. It only stings when it feels directly threatened, picked up, stepped on, or pressed against skin. This is one of the great surprises of working with the species. A bullet ant on a tree trunk observed from a foot away will often simply continue what it was doing. It might pause, it might lift its antennae, it might issue a soft chirp of warning, but it will not lunge, it will not pursue, it will not strike unless given a reason. To picture the temperament involved, imagine a bouncer at the door of a club. Quiet, watchful, capable of immense violence if necessary. Completely uninterested in causing trouble for its own sake. That is more or less the bullet ant's personality. This calm is in some ways what makes the ant so feared. Because when the bullet ant does strike, the strike is not the product of panic or aggression. It is a measured response. A decision. A precise application of the worst chemistry the insect world has produced. There is something almost philosophical about it. A creature that does not need to be cruel, that holds the most extreme weapon in its kingdom and does not waste it. The bullet ant simply walks through its forest doing what it has been doing for tens of millions of years, and it expects you gently to let it pass. Even the most painful ant on earth has to rest. Insect sleep is not the same as human sleep. There is no clear stage of unconsciousness, no equivalent of dreaming, no long, unbroken night. But ants, including bullet ants, do go through cycles of reduced activity that resemble rest. Periods when the body slows, the antennae go still, and the ant lies quiet within the nest. Studies of ant resting behavior conducted mostly on other species suggest that workers may take hundreds of very short rest periods throughout the day and night, each lasting only a few minutes. The total amount of rest added together can amount to several hours per day. The bullet ant, with its long lifespan and high energy demands, likely follows a similar pattern. There is something strangely tender about the idea. A creature whose name comes from the experience of being shot that has terrified rainforest visitors for centuries, quietly resting in the dark antennae, folded, surrounded by the soft chirps and movements of her sisters. Almost peaceful. The deepest rest periods seem to happen during the day when the colony is least active. Foragers who worked the previous night sleep through the heat, conserving energy for the next round of hunting. The queen rests almost constantly surrounded by her attendants in the deepest chambers of the nest. If you have ever watched a cat doze through the afternoon, that complete stillness broken only by the slow rise and fall of breath, you have seen something very close to how a bullet ant rests. Quiet, folded inward, waiting for the dark, because when the light fades, the work begins again, and the rest, brief as it was, will have been enough. The Schmidt Pain Index is the only formal scale used to rank the pain of insect stings. The bullet ant sits at the very top. It is rated 4.0 out of 4. The highest possible score, the maximum the index will record. The scale was developed by Justin Schmidt, an American entomologist over decades of personal experience. Schmidt allowed himself to be stung by more than 100 different species of insects across his career, bees, wasps, ants, and ranked the pain on a scale from 1 to 4. Most stings fall in the 1 to 2 range. A honeybee, for example, scores 2.0. A common wasp scores about the same. A few rare creatures reach 3.0. The tarantula hawk wasp, the warrior wasp. Both are notorious for their stings. The bullet ant scores 4.0. Some entomologists, including Schmidt himself, have suggested that the bullet ant would deserve a higher score if the scale allowed for one. There is, however, no 5.0. The scale was not designed to go that high because no one expected to find a sting so severe. To put the difference in perspective, the gap between a honeybee sting and a bullet ant sting on the index is not a small step. It is a different category of pain entirely. The way the gap between a candle flame and a house fire is not a matter of degree but of kind. Scientists and survivors still debate in casual conversation where exactly the bullet ant ranks in absolute terms. But there is no debate about the top of the official scale. That spot belongs completely to one creature. Justin Schmidt described many stings in detail, with a kind of dark poetry that earned him a quiet celebrity in entomology. He compared sting sensations to things ordinary people could understand. A bee sting was like a match head touched to skin. A bullet ant sting was something else. His most quoted description reads, "Pure, intense, brilliant pain, like walking over flaming charcoal with a 3-inch nail embedded in the heel." The pain, he wrote, can last over a full day, 12 hours, 20 hours, sometimes longer. Waves of throbbing agony rising and falling for hours after the moment of the sting, uncontrollable shaking, cold sweats. The body's nervous system, in his words, simply does not know how to process what is happening to it. Schmidt was not exaggerating for effect. He had been stung by nearly every venomous insect known to science. His comparisons came from direct experience. When he placed the bullet ant at the very top of his scale, he was not guessing. He had felt it. Other entomologists, who have been stung by bullet ants, sometimes accidentally, sometimes deliberately, for research, describe similar sensations. The pain is not just severe. It is unlike other pains. It is, to use a word people often reach for, indescribable. And yet they all reach for similar words: burning, throbbing, stabbing, a whole body sensation of being electrically wrong. There is something striking about reading these accounts side by side. The descriptions converge. Different researchers, different decades, different parts of the rainforest, they all come back with the same fragments of language, as if the bullet ant's venom produces in human beings a kind of universal experience. The bullet ant has, in a sense, written its own definition of pain. Inside the venom gland of a bullet ant lives a small, twisting molecule called ponerotoxin. It is named after Paraponera, the genus the ant belongs to, and it is, as far as science can tell, found in no other creature on Earth. Ponerotoxin is a peptide, a short chain of amino acids, that the ant produces inside specialized cells in its venom apparatus. The molecule is small enough to diffuse rapidly through tissue once it is injected. It is stable enough to last for hours inside the human body before being broken down. It is potent enough that an amount no larger than a grain of sand delivered into the right kind of nerve can cause the worst pain a person has ever recorded. The chemistry is in some ways surprisingly simple. Other animal venoms, those of snakes, spiders, or jellyfish, often contain dozens of different toxic compounds working together. Bullet ant venom contains ponerotoxin as the primary active ingredient. One molecule, one target, one result. Scientists studying ant venoms have noted that ponerotoxin is unique not only in its origin but in its structure. The way the molecule folds, the way it interacts with nerve membranes, there is nothing quite like it elsewhere in the chemistry of life. To picture it in scale, imagine a single key that fits a single lock, opening a door that human beings would generally prefer never to walk through. That is ponerotoxin. A single, exquisite, terrible molecule. The bullet ant carries it inside a venom sac no larger than a poppy seed. The sac is connected to a stinger barely longer than a pencil tip. The whole apparatus weighs almost nothing, and it has earned the ant its place at the top of every pain scale ever written. To understand what ponerotoxin does inside the human body, you have to understand how nerves work. Every nerve cell in your body communicates with the next by sending tiny electrical signals along its length. Those signals are generated by the rapid opening and closing of microscopic gates called sodium channels, small protein structures embedded in the membrane of the nerve. When the channels open, sodium ions rush in and the nerve fires. When they close, the nerve resets. Ponerotoxin attacks these channels. Specifically, the toxin binds to the sodium channels in pain-sensing neurons and locks them partially open. The nerves cannot reset. They continue firing over and over, sending an unbroken pain signal up the body to the brain. The brain, receiving this unrelenting cascade of distress, has no way to interpret it as anything but agony. Because there is no off switch, the pain does not pulse and fade. It pulses and fires again and again for hours. This is the difference between an ordinary insect sting and a bullet ant sting. Most venoms cause damage to tissue or trigger a brief immune response. Ponerotoxin does something more direct. It hijacks the nervous system itself. It makes the body produce its own pain continuously by overriding the mechanism that would normally turn pain signals off. If you have ever held your finger near a flame and pulled away, you have felt the system working as intended. Sharp signal, quick withdrawal, the pain fades. Now imagine the same signal repeating endlessly with no way to stop it. That is closer to what ponerotoxin produces. Scientists are still studying exactly how the molecule binds to sodium channels with such specificity. The findings may help explain not just bullet ant venom but pain itself. The bullet ant has a second nickname used widely throughout Latin America, Hormiga veinticuatro, in English the 24-hour ant. The name does not refer to the size or appearance of the insect, it refers to how long the pain lasts. A bullet ant sting does not fade in minutes. It does not fade in hours in the way most insect stings do. It lasts in the great majority of cases for roughly a full day, 12 hours. 20, sometimes longer, before the pain finally begins to recede. The intensity rises and falls in waves throughout that day. The first hour is often the worst, with the body in maximum shock. The next several hours bring a kind of plateau, relentless, terrible, but no longer increasing. By the second half of the day, the pain begins to soften, but it never fully releases. There are accounts of victims still feeling the sting site 24 to 48 hours after the original event as a deep throbbing ache. To picture the duration involved, imagine the worst pain you have ever felt in your life, lasting without break from sunrise on one day to sunrise on the next. That is roughly what a bullet ant sting feels like. This is part of why the bullet ant terrifies people in a way other insects do not. A wasp sting is sharp and quickly forgotten. A bullet ant sting is an event in the calendar, a day removed from the life of the person who received it. A day they will remember for the rest of their lives. Scientists studying ponerotoxin still debate exactly why the duration is so extreme. The molecule's persistence in tissue is part of the answer. So is the unusual way it binds. The mystery is not fully solved. In the world of stinging insects, there are three creatures that researchers and survivors consistently single out as carrying the worst pain. The bullet ant, the tarantula hawk wasp, the warrior wasp. These three are sometimes called half-jokingly among entomologists the three crowns of pain. The tarantula hawk wasp is a large metallic blue wasp found across the Americas, including the southwestern United States. Its sting is described as immediate blinding electric. Schmidt, who experienced it, called it a kind of running electric shock sensation. The pain is severe, but it generally lasts only a few minutes. The warrior wasp is found in the rainforests of Central and South America. Its sting in survivor accounts is similar to the bullet ants in intensity. Some have said it is even worse in the first moments, but again the pain tends to fade within a couple of hours. The bullet ant is the only one of the three that combines extreme intensity with extreme duration. The tarantula hawk burns hot and fast. The warrior wasp burns hot and lasts a little longer. The bullet ant burns hot and lasts an entire day. Imagine three very different fires. A flash of magnesium that blinds you for a few seconds, and a slow underground coal fire that has burned for years, unable to be extinguished beneath the floor of a town. The bullet ant is the underground fire, the one that will not stop, the one that smoulders long after every other flame would have gone out. It is why among the three crowns of pain, the bullet ant tends to be the one researchers respect the most. Anyone can be stung once and recover. Not everyone can survive 24 hours of it. The name bullet ant did not come from scientists. It came from people who had been stung. Local guides, field researchers, indigenous hunters. They all reached for the same word in different languages because no other word fit what the experience felt like. The sting is, in the first instant, a sharp, hot, sudden impact. There is almost no warning. The mandibles grip, the stinger drives in, and the pain that follows arrives in the survivor's perception as fast as a gunshot. Anyone who has been shot accidentally in war, in a hunting accident, and then later been stung by a bullet ant tends to agree. The two sensations are different in kind but similar in shock value. Both arrive faster than the brain can process. Both make the body buckle. Both produce a kind of disbelief in the first few seconds that anything could hurt that much. This is why the name has held for more than a century. People keep trying to come up with a better one. They keep failing. Some have tried lesser giant hunting ant, the literal English of one scientific name. It is descriptive, but no one uses it. Some have tried the 24-hour ant, which is accurate, but does not convey the moment of impact. Some have tried simply the worst ant. No one believed them until they were stung themselves. The name bullet ant survives because it tells the truth about the first second of the experience. The rest of the day is harder to name. But that first instant, that single terrible moment, is unmistakable. You are not bitten. You are not pricked. You are not stung in the ordinary sense. You are shot. The bullet ant carries different names across the rainforest cultures of South America, and each one tells you something about the relationship between the people and the insect. In the Amazon basin, it is called Isula by some indigenous groups. In Brazilian, Portuguese, Tocandera or Tucandera, names with deep roots in the languages of the original peoples of the region. In Spanish-speaking countries, Hormiga, Veinticuatro, and Conga, each name carries a small story. Isula evokes the dark places where the ant is most often found. Tocandera in some Tupi languages has been translated as one who wounds deeply. Tucandera, the form used in the famous initiation ritual, carries a weight of cultural meaning that goes beyond the insect itself. There is also a less formal collection of names used by outsiders: the bullet ant, the 24-hour ant, the lesser giant hunting ant in older literature, sometimes even the kapok ant, after one of its host trees. These names tend to come from explorers, scientists, and travelers, people who needed a way to describe the creature in a language other than its own. What is striking is that almost every name in every language contains some hint of the sting. Even the names that refer to size or color or habitat tend to come with a warning attached. There is no language anywhere in the rainforest world that has chosen to forget what this ant can do. Researchers studying indigenous knowledge of insects have noted that the bullet ant is one of the few species whose cultural names are remarkably consistent across unrelated languages. The peoples of the Amazon, separated by hundreds of miles and centuries of history, all came to roughly the same conclusion. This ant is something to name carefully. And to remember, the pain of a bullet ant sting is not just felt as pain, it is felt as a full-body event. One of the most striking symptoms reported by victims is uncontrollable, shaking, sometimes mild trembling, sometimes severe convulsions that can last for hours. The shaking is not voluntary. It is not the kind of trembling you might do when you are cold. It is the body's nervous system, overloaded by the relentless firing of pain signals beginning to misfire elsewhere. Muscles contract and release without instructions. Limbs jerk. Hands shake. In severe cases, the entire body becomes briefly impossible to control. This is part of what makes the bullet ant sting so unsettling, even to people who have experienced other intense pains. Most pain stays where the injury is. Stub your toe and your toe hurts. Cut your hand and your hand hurts. A bullet ant sting reaches up through the entire body through nerves and muscles far from the site of the wound and disrupts the body's coordination as a whole. To picture the experience, imagine the way your hand shakes after a very strong electric shock, that uncontrolled low-frequency tremble that is not under your command. Now imagine it spreading to your arms, your legs, your jaw. Now imagine it lasting for hours. Researchers studying the effects of ponerotoxin have suggested that the shaking is the direct consequence of the toxin's interference with sodium channels in motor neurons. The same molecule that causes the pain is also disrupting the body's ability to control its own movement. The shaking eventually fades as the body slowly metabolizes the venom. But for the first several hours after a sting, the victim is not entirely in command of their own body. Beyond the pain and the shaking, a bullet ant sting often produces a constellation of other symptoms. Cold sweats, heavy sweating that comes in waves soaking the skin without warning, nausea, sometimes mild, sometimes severe enough to cause vomiting, a racing, irregular heartbeat, dizziness, in some cases brief loss of coordination or even fainting. These are not allergic reactions in the classical sense. They are the body's general response to extreme nervous system overload, the same kind of response you might see in someone who has just been through a severe physical trauma or shock. The body, unable to make sense of the signal it is receiving, simply throws every alarm it has. The heart, in particular, can behave strangely. Some victims report a pounding, accelerated pulse for hours. Others report the opposite, a slow, heavy thudding as if the heart is unsure what tempo to keep. The autonomic nervous system, which normally manages heart rate and breathing without conscious thought, has been thrown off balance. For most healthy adults, these symptoms pass within a day. The body recovers, the heart returns to its rhythm, the sweating stops, the nausea fades. The sting site, sometimes for several more days, remains tender and slightly swollen. For someone with a pre-existing heart condition, or for very young or very old people, the experience can be more dangerous. The bullet ant sting is rarely fatal in healthy adults, but the cardiac stress it produces is not nothing. Several documented cases over the years have involved hospitalization, particularly when multiple stings were received at once. This is a creature whose chemistry in a single drop can briefly rewrite the operating instructions of the human body. Almost everyone has been stung by a honeybee at some point. A sharp, sudden burn, a red welt that swells, a few hours of discomfort, then it fades and you forget about it within a day or two. To anyone who has been stung by a bullet ant, that experience feels almost like a memory of pain rather than pain itself. The difference is not just intensity, it is duration, character, and the depth of the body's response. A honeybee sting affects mostly the skin and local tissue around the wound. A bullet ant sting affects the entire nervous system. A honeybee sting fades in hours. A bullet ant sting fades in a day, sometimes longer. To picture the gap between the two, imagine the difference between a kitchen burn from a hot stovetop and being trapped in a small room with a furnace door slightly open. The first is a sharp, contained event. The second is an environment. The body experiences each one in a completely different way. Victims of bullet ant stings in the days afterward often describe minor pains, paper cuts, stubbed toes, ordinary headaches as feeling almost pleasant by comparison. The body, having endured something so far outside its normal range, briefly recalibrates what it considers painful. A small ache for a few days becomes almost a comfort. The bullet ant has not made other stings less painful. It has only made everything else feel smaller. If you have ever survived a serious illness or injury, you may know the feeling. There is a strange peace that comes from having been through something worse than what is in front of you right now. Bullet ant survivors describe a version of this. The pain teaches a kind of perspective. It is, in its terrible way, a teacher. Long before scientists understood the chemistry of ponerotoxin, European naturalists were already writing about the bullet ant in the same tone of awe and dread that the indigenous peoples used. The first detailed descriptions came from explorers and missionaries traveling through the Amazon in the 17th and 18th centuries. Hans Sloane, the English physician and naturalist, described painful tropical ants in his early collections. Later, Henry Walter Bates, the British naturalist who spent 11 years in the Amazon in the mid-1800s, wrote about being stung by what was almost certainly a bullet ant. His account describes a sting so violent that he was forced to stop work for the entire day. He compared the sensation to a deep wound well beyond anything he had previously felt from an insect. Later in the 19th century, German and French biologists collecting specimens in the Amazon also began describing the species in detail. Each account independently emphasized the same things: the size of the ant, the strange chirping sound it made, and above all, the pain of the sting. By the early 20th century, the bullet ant had developed a reputation among European entomologists as the worst stinging insect known to science. The pain scale that would eventually formalize this ranking, the Schmidt Pain Index, was still decades away. But the conclusion had already been reached by men who had felt it themselves. What is remarkable looking back at these old field notes is how consistent the descriptions are. Different naturalists, different nationalities, different decades, they all converge on the same fragments of language, the same shock at the duration, the same disbelief at the intensity. The bullet ant has in a way been making the same impression on people for as long as written records of the rainforest exist. A bullet ant sting does not stay at the sting site. Within minutes of the venom being delivered, it begins to travel. The pain moves, spreading outward from the wound, following the lymphatic system as it goes. For a sting on the hand or forearm, which is the most common location, victims often report the pain moving up the arm toward the elbow and armpit within the first hour. The lymph nodes in the armpit, the stations of the immune system closest to the wound, swell. They become tender to the touch. In some cases, they become visibly swollen, detectable by pressing gently along the inside of the arm. This is the immune system attempting and largely failing to contain something it has no defense against. Ponerotoxin is not a bacterium. It is not a virus. It is a molecule that the body's defenses were never designed to stop. The lymph nodes can filter out many things, but a neurotoxin that acts directly on nerve membranes does not belong to any category of threat the human body is built to intercept. The swelling along the arm, that slow, warm march of inflammation from wrist to armpit, is one of the most frequently described secondary effects in victim accounts. It is not dangerous in itself, but it is a vivid illustration of what is happening inside the body. The venom is moving. The body is chasing it. Scientists debate exactly how much of this inflammatory response is triggered directly by ponerotoxin and how much by other compounds present in bullet ant venom in smaller quantities. The full chemistry of the venom has not yet been completely mapped. Among the more unsettling accounts of bullet ant stings are those that include hallucinations. Not every victim reports them, perhaps not even most, but enough do that researchers have paid attention. The reports are consistent in their strangeness: dark shapes at the edges of vision, brief, vivid moments of unreality, a sense of detachment from the body. In a few documented cases, temporary confusion severe enough to leave a person unable to remember where they were or what had happened to them. Whether these effects come from ponerotoxin itself or from the body's extreme stress response to the pain is still not fully understood. Some researchers suggest the brain, flooded with pain signals on a scale it has never encountered, may temporarily lose coherence in other areas as a side effect. Others suggest the hallucinations are the result of hyperventilation, which often accompanies extreme pain and can produce its own visual and cognitive disturbances. A third possibility, more speculative, is that some secondary compound in the venom crosses the blood-brain barrier and produces mild psychoactive effects in certain individuals. This hypothesis remains contested. Scientists have not yet identified such a compound with certainty. Whatever the cause, the accounts exist. Field researchers, indigenous elders, documentary subjects who have experienced the sting have described these moments with varying degrees of certainty. They do not claim to have seen visions in any spiritual sense. They describe simply losing briefly their grip on what was real. For an animal the length of a thumbnail operating through a molecule smaller than a grain of sand, this is a staggering reach. Over the decades, people who have been stung by bullet ants have tried to explain the pain to those who have not. The comparisons they reach for reveal something about the limits of language when confronted with extreme sensation: broken bones. Several victims, including some who have fractured limbs in accidents, have said the bullet ant sting is worse. Not because the tissue damage is greater, the sting leaves almost no physical wound, but because the pain signal is more unrelenting and more comprehensive than a fracture tends to produce. Childbirth. This comparison has been made with some caution by a small number of women who have experienced both. The consensus where there is one tends to be that the sensations are different rather than directly comparable. Childbirth pain tends to pulse in waves with recovery between them. A bullet ant sting provides no recovery between waves. Electric shock. This may be the comparison that most survivors reach for most often. The penetrating whole-body character of the pain, the way it does not stay where the wound is, maps most closely onto what people describe when they discuss accidental contact with high-voltage current. Scientists who study pain as a discipline have noted that different categories of pain are processed through different nerve pathways. The fact that bullet ant victims consistently compare the sting to electric shock rather than to burning or cutting tells them something about which pathways ponerotoxin is most aggressively stimulating. The body does not just experience the pain, it files it into a category. And the category it reaches for again and again is the most electric, most systemic, most whole-body kind of pain the human nervous system knows how to name. One of the most common questions people ask about the bullet ant is a simple one. Can it kill you? In healthy adults, the answer almost universally is no. A single bullet ant sting, painful as it is, does not deliver enough ponerotoxin to cause life-threatening organ failure or nerve damage in a person of normal weight and health. The venom is extraordinarily effective at producing pain, but it is not designed in an evolutionary sense to kill large mammals. It is designed to make them leave. From the ant's perspective, this is the point. A predator that has been stung and retreated is a lesson learned. A predator that has been killed becomes something more complicated, something that might attract scavengers, disrupt the nest, draw attention the colony does not want. The goal of the bullet ant's venom has always been deterrence, not destruction. Survivable is not the same as trivial. Survivable does not mean forgotten. Survivable does not mean the body is unchanged. It means the person lives. It means they get through the next 24 hours. It means when the pain finally lifts, they find themselves still present, still breathing in roughly the same forest they were in before. Minus one very difficult day. The calculation that makes a single bullet ant sting survivable begins to break down when the stings multiply. A single sting delivers a measured dose of ponerotoxin to one location on the body. The nervous system is stressed, but not overwhelmed beyond recovery. 2 stings, double the dose, and double the affected area. 3, 4, 5 stings escalate the stress exponentially. The compounding effect of ponerotoxin from multiple sites is not merely additive. The neurotoxin disrupts the body's ability to manage itself, and as the disruption spreads, the body loses its ability to compensate. Several documented cases of individuals receiving multiple stings at once from accidentally disturbing a nest have resulted in hospitalization, severe convulsions, temporary paralysis of limbs, cardiac arrhythmia lasting hours. To picture what multiple stings feel like, imagine the worst headache you have ever had spreading rapidly across your entire nervous system with no possibility of lying down in a dark room and waiting for it to pass. That is at minimum what the early stages of a multi-sting event produces. Indigenous guides who work with bullet ants on a daily basis have developed over lifetimes a careful respect for this threshold. They know the difference between a single, unexpected sting, which is painful but managed and disturbing, a colony which is a different category of event entirely. One is an accident. The other is a crisis. In a rainforest hours from the nearest medical facility, the difference matters enormously. The bullet ant in multiples becomes something the human body was genuinely not built to survive without consequence. For most people, a bullet ant sting is an experience of pain, not a medical emergency, not a mortal threat. Just the longest, worst day an insect has ever given anyone. For a small number of people, it is something else. Anaphylaxis, the severe systemic allergic reaction that can follow exposure to insect venom, has been documented in bullet ant sting cases though far less frequently than with bee or wasp stings. The reaction occurs when the immune system, instead of simply battling the venom, overreacts to a protein in the venom, as if it were an existential threat. Airways narrow. Blood pressure drops. The body attempts to fight a battle that is actually against itself. For someone experiencing anaphylaxis from a bullet ant sting, the pain already, the worst they have ever felt, becomes secondary to a suddenly life-threatening respiratory event. The medical community's understanding of bullet ant venom allergy is still developing. Far fewer people are stung by bullet ants than by honeybees, which means the data on allergic responses is limited. Scientists still debate whether the reactions reported in documented cases are true anaphylactic responses to ponerotoxin specifically, or to other less understood compounds present in the venom. What is known is that for anyone with a history of severe insect sting allergy, the bullet ant presents a serious risk. For anyone else, the risk is small but not zero. The bullet ant is in the end a creature that operates at the outer edge of what a human body can tolerate. Most people clear that edge by a narrow margin. A few do not. In the entire world of venomous insects, honeybees, wasps, hornets, fire ants, harvester ants, velvet ants, no venom works quite the way ponerotoxin does. Most insect venoms are cocktails of enzymes, proteins, and peptides working together. They destroy tissue. They trigger immune responses. They cause swelling, redness, cell death. Some, like the venom of certain hornets, attack red blood cells directly. Others, like the venom of fire ants, are mostly cytotoxic. They kill cells at the sting site. Ponerotoxin does something different. It is a neuroactive peptide. Its primary effect is not on tissue, not on cells, but directly on the electrical signaling of nerves. It belongs to a family of molecules found scattered across the natural world in things as different as cone, snail, venom, and certain fungi that have independently arrived at the same target, the sodium channel. But the specific molecule the bullet ant produces is not replicated anywhere else. This uniqueness has made ponerotoxin an object of intense scientific interest, particularly in the field of pain research. A molecule that can produce such extreme, consistent, prolonged pain in human beings is paradoxically a research tool of great value. It allows scientists to study pain pathways in ways that other compounds cannot replicate. To picture why that matters, imagine trying to understand how a fire alarm system works by studying only the faintest trace of smoke. Now imagine being handed a fire so intense it sets off every alarm in the building at once. That is, scientifically speaking, what ponerotoxin gives researchers. A signal so clear and so powerful that the pathways it lights up become possible to map. Evolution does not produce cruelty. It does not design suffering for its own sake. When a creature develops a weapon as extreme as ponerotoxin, there is always a reason rooted in survival. The most widely accepted explanation is defense. The bullet ant colony, small in number, slow to reproduce, nesting in a fixed location that cannot easily be abandoned, needed a deterrent powerful enough to discourage any predator from making the same mistake twice. A sting painful enough to last 24 hours achieves this very efficiently. An animal that attacks a bullet ant colony once will almost certainly never do it again. The cost of the memory is too high. A secondary theory, less tested, is that the extreme pain may also help the bullet ant in competitive interactions with other ant species. In a rainforest where many colonies compete for the same nesting sites, a colony capable of delivering such a devastating sting has a powerful advantage in territorial disputes. A third possibility, still at the level of hypothesis, is that the venom's properties may also serve in prey capture. Most insects once stung by ponerotoxin are rapidly incapacitated. For a solitary forager hunting alone, a venom that kills prey quickly is an enormous practical advantage. Scientists are still debating which of these pressures drove the evolution of ponerotoxin and in what combination. The answer, when it eventually arrives, will reveal something important, not just about the bullet ant, but about how extreme weapons emerge in the natural world. The brutality of the venom is not random. It is in its own dark way elegant. There is a people living in the heart of the Brazilian Amazon, whose name for themselves means the stinging ant people. the Sateré-Maoé, a nation with a history stretching back long before the first Portuguese ship arrived on the coast of Brazil. They live today in a territory of protected rainforest along two rivers, the Andirá and the Marão, in the state of Amazonas. Their villages are small, their language is distinct. Their traditions are carried forward through generations with a care that comes from knowing how easily the modern world can erase what it does not understand. The Sateré-Maoé are farmers, fishermen, and guardians of one of the most biodiverse regions remaining on Earth. They are also for reasons that have made them subjects of documentaries and scientific studies and visits by foreign journalists. The people who built one of the most demanding coming-of-age rituals on the planet, a ritual built around an ant. Their relationship with the tucandera, the bullet ant, is not merely practical. It is not simply that the ant lives in their territory. It is that the Sateré-Maoé have chosen deliberately and over many generations to make the ant a gateway, a test, a doorway through which boys must pass in order to become men. If you have ever wondered what it means to belong completely to a place, to know its animals, rivers, and seasons not as facts but as life, the Sateré-Maoé offer one answer. They have been living alongside the bullet ant for longer than most nations have had names. They know something about it that science is still learning to ask. The territory of the Sateré-Maoé lies in a remote crescent of the Brazilian Amazon, bounded by the wide, dark rivers that give their land its shape. The Andirá to the north, the Marão to the south. Between them, a stretch of primary rainforest covering roughly 10,000 square kilometers, an area close to the size of the state of Connecticut, that has been home to the Sateré-Maoé for generations beyond counting. The forest there is old, not old in the sense of having survived a few centuries of colonial pressure, though it has survived that too. Old in the deeper sense, ancient in its structure, layered in its canopy, rich in the slow, dark soil that only forms when a forest has stood in one place for a very long time. The kinds of trees that bullet ants prefer, the kinds of root systems in which bullet ant colonies settle and live for decades. In this forest, the Sateré-Maoé have developed a detailed, intimate knowledge of the insects around them. They know which plants the bullet ant favors. They know the times of year when foragers are most active. They know the soft stridulation chirp that local guides across the Amazon treat as a final warning. And they know, perhaps more deeply than anyone else on Earth, what happens to a human body that spends 10 minutes wearing a glove lined with living bullet ants. That knowledge was not gained through observation alone. It was gained through experience, repeated, chosen, endured, and carried forward generation by generation through a ritual that has survived everything the last 500 years have thrown at it. In many cultures around the world, there is a moment that separates childhood from adulthood, a ceremony, a test, a threshold that must be crossed before the community recognizes a young person as having arrived at the responsibilities and standing of a grown person. Among the Sateré-Maoé, that threshold is built from bullet ants. The ritual is called, in some accounts, the Tucandera dance. Its purpose is not punishment. It is not cruelty. It is, in the logic of the culture, a gift, the hardest gift an elder can give to a young person, the gift of having endured something real. The Sateré-Maoé live in an environment that demands a particular kind of strength. Not physical strength alone, though the rainforest requires that too, but the capacity to face pain, fear, and uncertainty without losing composure, without running, without letting the body's panic override the mind's steadiness. These are the qualities that keep a community alive in a place where the forest is, simultaneously a home and a test. The initiation ritual does not merely celebrate these qualities, it produces them, or rather it reveals whether they are already present in the young person who enters the circle. A boy who can wear a glove of bullet ants for 10 minutes, moving and dancing without crying out, has proven something about himself. Not just to his community, to himself. And that knowledge carried inside the body rather than simply spoken about is the kind that does not fade. The ritual is not about pain. It is about what a person discovers on the other side of it. The glove itself is a remarkable object, woven by hand from the leaves and fibers of plants found in the surrounding forest. It takes the general shape of a sleeve wide enough to accommodate an adult hand and wrist deep enough to extend partway up the forearm. The weaving is tight and deliberate, with the inner surface lined so that the ants placed inside cannot escape, but can move freely enough to flex and sting. The making of the glove is not incidental to the ceremony, it is part of it. Elders of the community spend time gathering the materials, weaving the form, and preparing the vessel that will carry the ants. The glove is made with the same attention given to anything that plays a formal role in the community's spiritual life. From the outside, the finished glove looks like a thick, dark, somewhat crude mitten, fibrous and woven without ornamentation, without the finish of a tool meant to be admired. It is not meant to be admired. It is meant to be worn. You might find something that resembled it in a craft market without knowing what it was for. It is only when you understand what will be placed inside it, and that a young boy will press his hand into it, that the object begins to carry its true weight. The glove holds no power of its own. It is woven grass. It is plant fiber. It is the shape of something that could be used for anything. The glove is just a vessel, but the vessel holds something that changes the person who wears it. To prepare the glove for the initiation, the bullet ants must be placed inside, with their stingers facing the hand that will eventually wear it. Not outward toward the outside world, inward toward the skin. This is not accidental. It is the point. The ants are woven into the inner lining of the glove, pressed in carefully by the elders, sometimes dozens of individuals, sometimes closer to 100 depending on the season and the local availability of workers. Each ant is oriented with its abdomen and therefore its stinger facing the center of the glove. When the wearer slides their hand inside, they are sliding it into a chamber lined with live insects pointed directly at their skin. The image is viscerally difficult to sit with even at a distance. Most people, upon hearing this description, feel something: a sympathetic recoil, a tightening of the forearm, a small involuntary gesture of protection. That response is the body's own wisdom speaking. It knows without being told what a glove full of bullet ants would feel like. And yet the boys of the Satere Mawe have been entering that glove willingly for generations. Anthropologists studying the ritual have noted that the inward orientation of the stingers is essential to the symbolic logic of the ceremony. The point is not simply to be near the ants, the point is to be inside their reach, to offer the hand deliberately into the space where pain is already waiting. That is a different act than being stung by accident. It is a choice, made with open eyes, and chosen again every time the glove is put on. Before the ceremony begins, the bullet ants must be collected from the forest and prepared. This is done carefully and with considerable skill. Workers from nearby colonies are gathered, sometimes over a period of days, sometimes in a single concentrated effort, using techniques refined across generations. The collectors work at night or in the early morning when the ants are less active, using containers made from natural materials to transport the insects back to the village. Once gathered, the ants are submerged briefly in a natural herbal mixture. The plants used in this preparation vary by community and are considered in some accounts to be traditional knowledge not fully shared with outside researchers. What the preparation does broadly is sedate the ants, temporarily lowering their activity enough to allow the elders to handle and position them within the glove without triggering mass stinging. The sedation does not last. This is crucial. The ants are not permanently affected by the herbal immersion. They are slowed, quieted, made briefly manageable, and then placed. Scientists studying this preparation have expressed interest in which specific plant compounds are responsible for the sedating effect, and whether those compounds might have broader applications in entomological research. But the details remain in most communities closely held. Historians and anthropologists still debate how much of the Satere Mawe's botanical knowledge has been fully documented and how much has already been lost to the pressures of the modern world. The herbs that quiet the ants before the ritual carry their own kind of knowledge, ancient, specific, hard-won, shared only with those who have earned the right to know. When the boy slides his hand into the glove, the ants begin to wake. The warmth of the human hand rouses them from the sedation. The pressure of the hand moving into the sleeve disturbs their stillness, and the chemical signature of a living, frightened animal, the pheromones of stress that the human body releases when it is under threat, is for the ants the clearest possible alarm signal. They do not need to be provoked further. The hand itself arriving into the space where they have been placed is sufficient. They sting. Not all at once in a coordinated attack. Bullet ants do not behave that way. But one after another, as each ant in the lining of the glove contacts the skin or detects the heat and chemical signals of the hand near it. The stings come fast. They come continuously. And they come from every direction at once because the hand is surrounded on all sides. To sit with that image, to really allow it, is to feel something like awe at the person who keeps the hand inside. There is no trick to it. There is no preparation that prevents the pain. There is only the boy's decision in each passing second to keep the hand where it is. That decision made dozens of times over 10 minutes in the presence of the entire community, with the memory of all who came before, pressing quietly on the moment, is the real heart of the ritual. The duration of the ritual is 10 minutes, not an hour, not a day. 10 minutes. To anyone who has felt a single bullet ant sting, this figure lands differently than it would otherwise, because a single sting from a single ant begins a 24-hour ordeal. The glove contains dozens of ants, sometimes more than 100 stinging, continuously across the full duration of wear. The total number of stings received in one wearing can number in the dozens, each one delivering ponerotoxin into the skin of the hand and wrist, each one beginning its own rolling wave of pain on top of all the others already underway. The 10 minutes are not chosen arbitrarily. They are the result of centuries of practice, a duration long enough to constitute a genuine ordeal, short enough to be survivable without permanent physical damage in the overwhelming majority of cases. The tradition is not designed to destroy its participants. It is designed to test them. A marathon asks for endurance over distance. The glove asks for steadiness inside a storm. They are entirely different demands on an entirely different part of a person. Researchers who have observed the ceremony describe the 10 minutes as the quietest part of the day. The village gathers, the community watches. Almost no one speaks. The silence around the ordeal is as much a part of the ritual as the pain itself. Historians and anthropologists still debate exactly how long this specific 10-minute duration has been practiced, and whether earlier forms of the ritual may have varied in length or structure. The written record extends only a few centuries. The practice itself reaches back much further, 10 minutes, across centuries. Because the Satere Mawe have learned across generations that there are things a person can only know by going through them, and that the glove, with its live cargo and its 10 unbearable minutes, teaches the one thing no elder can explain in words alone. The boy does not simply stand still and endure the glove. He dances. The dance is not elaborate. It is a structured movement, a slow, rhythmic stepping and swaying that the boys learn before the ceremony and must maintain throughout the wearing of the glove. Stopping the movement is not permitted. Standing frozen is not permitted. The dance must continue. This requirement is not accidental. It serves several purposes within the ritual's logic. A moving body demonstrates a level of composure that a still body cannot. To stand and absorb the pain is an act of endurance. To move to maintain rhythm, to perform even the smallest coordinated gesture, while the nervous system is being overwhelmed from every direction, that is something closer to mastery. The elders and community members who watch the ceremony are watching the dance as much as they are watching the face. How the boy moves tells them more than his expression. Does he keep the rhythm? Does the stepping stay even? When the pain rises to its worst point, does the body still hold its form? There is a kind of beauty in the discipline this requires, a beauty that is hard to describe to someone who has not seen it. What might look in another setting like a simple shuffle step in a village clearing becomes here the most difficult thing a young person has ever been asked to do. And he does it, dancing, while the elders watch, while the community breathes together, while the forest holds its particular silence, and the ants do what the ants have always done. A single wearing of the glove is not enough. The ritual is not a one-time passage. To be fully recognized as a man among the Satere Mawe, a boy must complete the ceremony 20 times. 20. The wearings are spread across months and years, with time between for the body to recover and for the young person to grow into their understanding of what they are doing and why. The first wearing typically happens in early adolescence. The last may happen years later in young adulthood. By the time the 20th wearing is complete, the person who steps out of the circle has done something very few human beings in history have done. They have, by deliberate choice, been stung by bullet ants more than 1,000 times. The count is not what matters in the logic of the Satere Mawe. It is not about accumulating pain. It is about returning, about choosing again and again, knowing what is inside the glove to put the hand in anyway. That choice, made with full knowledge, full memory across years of life, is what the tradition is built to produce. Not endurance in a single moment. Endurance as a way of living. Anthropologists who have studied the ritual across multiple generations of Satere Mawe participants note that the men who have completed all 20 wearings carry a quality that is noticeable. Not the silence of damage, not the numbness of someone who has simply stopped feeling. Something more like the stillness of a person who has settled deeply and permanently into knowing what they are made of, and who no longer needs anyone else to tell them. There is no fixed age at which a Satere Mawe boy wears the glove for the first time, but in most accounts gathered by anthropologists and documentary filmmakers who have spent time with the community, the first wearing tends to happen somewhere in early adolescence, typically around 12 to 14 years of age, sometimes slightly older. This is not a decision made by the boy alone. It is made in conversation with his family, with the elders of the community, and with the boy himself across a period of preparation that can begin years before the actual ceremony. The boy knows what is coming. He has watched the ceremony happen to others. He has heard accounts from men who have already completed it. He chooses, with that knowledge, to step forward. The preparation is partly physical, a general readiness for the ordeal ahead, but it is also cultural. The elders speak to the young people about the purpose of the ceremony, about what it asks of them and what it gives back, about the men who came before and what the ritual meant to them. By the time a boy stands at the edge of the circle for the first time, he is not ignorant of what he is walking into. He simply has not felt it yet, and there is a limit to what any amount of watching and listening can do to prepare a person for the first moment the glove closes around the hand. For the first sting, for the realization that everything he has been told is true. That moment, however it lands, is his alone. No elder can carry it for him. No word has ever fully described it. When the ceremony ends and the glove comes off, the ordeal is not over. The stings received across 10 minutes of wear do not fade gently. The venom delivered by dozens of stings across the hand and wrist begins in the hours after the ceremony to produce its full effect. The arm swells. The fever rises. The shaking begins, the same uncontrollable trembling that single sting victims report, but multiplied across a vastly greater dose. For the first day after the ceremony, some participants cannot fully use their hands. The fingers may curl involuntarily. The arm may be painful to move. In some accounts, participants describe temporary numbness alternating with waves of intense pain as the ponerotoxin is slowly metabolized from the tissues. Some sleep poorly for 2 or 3 days. Some run fevers that linger. Some describe dreaming of the ceremony, the ants, the dance, their body still processing in sleep what the nervous system experienced while awake. If you have ever woken after a difficult ordeal and felt in the first quiet morning that something had shifted in you, some small addition to the self you carried, before you have felt a pale echo of what the Satere Mawe describe in the days after the ceremony, the body heals. The fever breaks. The hand opens again slowly over the course of a few days. What remains after the healing is complete is something that does not go away. Not pain, not damage, something quieter and more permanent. The knowledge held now in the body, and not just the mind, of what the person was able to choose and choose again until the choosing itself became who they were. The word endurance carries different meanings in different cultures. In the modern world, we often speak of it in the context of sport, the athlete who crosses the finish line despite pain, the marathon runner who pushes through the wall. Endurance in this framing is a personal achievement, a triumph of will over discomfort sealed between an individual and their own body. Among the Satere Mawe, endurance is something else entirely. Not a personal achievement, a social fact, a contribution to the community, a way of demonstrating that the person who stands before the group is capable of the steadiness the group requires. The distinction matters because it changes what the ritual is for. A Satere Mawe boy wearing the glove is not in the tradition's own logic doing it for himself. He is doing it in the presence of everyone he will ever live with, in the presence of elders who did it before him, peers who will do it alongside him, and younger children who are watching and learning in this moment. What it means to be a person in this community. The community does not merely witness the ceremony, it holds it. The watching, the silence, the gathered presence of the people, all of it is weight added to the moment. All of it is what transforms an act of private suffering into a public declaration. This is what cultures that have lived close to the land for thousands of years often understand about endurance that more insulated cultures can lose sight of. It is not about defeating the pain. It is about what a person proves to the people who will share their life. At the center of every Tukandera ceremony is a figure who rarely draws attention to himself. The Peye, the shaman of the Satere Mawe, presides over the ritual not as a performer or a judge, but as a guardian, a keeper of the form. The Peye stands in relation to the ritual, the way a witness stands in relation to a serious and binding event, not the subject, not the authority, but the one whose presence makes the proceedings real. He oversees the preparation of the ants and the glove. He leads the prayers and ceremonial songs that open the ritual. He monitors the boy throughout the wearing, watching not for weakness, but for signs that the physical ordeal has crossed into genuine medical danger. He is both spiritual authority and practical protector. Among the Satere Mawe, the Peye holds a role that extends far beyond the initiation ritual. He is a healer, a keeper of traditional knowledge, a mediator between the community and the forest. His knowledge of plants, including those used to sedate the ants before the ceremony, is extensive and in many cases not written down anywhere. It lives only in him and in those he chooses to teach. Researchers still debate how much of the traditional knowledge held by older Peye has been successfully transmitted to younger generations, and how much has already been lost in communities that have had extended contact with the outside world. He does not speak during the boy's wearing of the glove. He watches. That watching is its own kind of language, and the boy knows throughout that the Peye is there. When a boy wears the glove, his entire community gathers to witness the ceremony. This gathering is not incidental. It is required. The Satere Mawe do not perform the Tukandera as a private act. There is no version of the ritual that happens quietly away from the eyes of the community. The watching is part of the structure. The silence of the gathered people is not the absence of sound. It is itself a form of support, a form of witness, a form of pressure that shapes what the moment means. The elders who have completed all 20 wearings are present. They do not need to say anything. Their presence says it already. The younger children who have not yet undergone the ceremony are present too, watching, learning, forming in this moment their first clear understanding of what will eventually be asked of them. The mothers of the boys are present. Accounts gathered by anthropologists describe the particular composure required of families during the ritual to watch a child endure pain without intervening, without calling out, without moving to comfort them, requires its own kind of endurance from those who love them. It is in its way a test the whole community takes together. Most of us have been in some version of that position, standing beside someone in pain we cannot take away, choosing to remain present even when presence feels insufficient. The Satere Mawe understand perhaps more deeply than most that standing beside is never nothing, that the held breath of a community breathed slowly together, waiting for the 10 minutes to be over, is its own language of love. The boy in the circle knows the whole community is with him. Among the Satere Mawe, the men who have completed all 20 wearings of the glove occupy a particular place in the social fabric of the community. Not a title exactly, not a rank in any formal hierarchy, something more organic than either of those. They are known. Their history with the glove is part of how the community understands who they are. When decisions need to be made about the forest, about the village, about conflicts with neighboring communities or pressures from the outside world, the men who have completed the ritual carry a weight in those conversations that comes from something beyond argument or seniority alone. It comes from the fact that the community watched them endure something almost unendurable, repeatedly, voluntarily, without flinching from the circle. This is not political power in any Western sense. It is a different kind of authority, one rooted not in office or inheritance, but in what the person has demonstrated they are capable of in the most demanding conditions their culture has designed. The community knows what they chose. The community was there. Anthropologists studying the social structures of Satere Mawe communities have noted that the moral authority of men who have completed the full cycle of the Tukandera tends to be informal but real, respected without being enforced, sought without being demanded. To picture the kind of standing this produces, imagine the difference between a person who has read about a difficult thing and one who has lived through it. Both may speak, but the room listens differently, and the community which was present for every one of the 20 knows exactly which person is which. The Tukandera ritual first entered the written record of Western observers in the accounts of European missionaries and colonial administrators traveling through the Brazilian interior in the 18th and 19th centuries. These accounts are fragmentary and often distorted by the assumptions of the people writing them. The early descriptions of the ceremony read today have the quality of a sketch next to a portrait. The outline is present, but the meaning is missing. Some observers describe the ritual with a mixture of horror and bewilderment that says more about the writers than about the Satere Mawe themselves. They had no framework for understanding why a community would build voluntary suffering into the structure of growing up. Later accounts from the late 19th and early 20th centuries began to apply the more systematic methods of emerging anthropology. Field workers who spent longer periods with the Satere Mawe documented the ritual in greater depth, its structure, its timing, its relationship to the broader ceremonial life of the community. These records form the backbone of what the academic world knows about the Tukandera today. Historians studying the record still debate how much of the ritual's original form is captured in these early documents, and how much was already changing by the time outside observers arrived to describe it. The Satere Mawe had been practicing the ceremony for generations before anyone wrote it down. What was recorded was already, in some sense, a translation. What was present in every account, regardless of the observer's sympathy or understanding, was a single stubborn fact. The boys wore the glove, and then they wore it again. In the decades since documentary filmmaking found its way into the remote corners of the Brazilian Amazon, the Tukandera ceremony has been recorded by cameras from several countries. And in some of those documentaries, the filmmakers or hosts did not just record the ritual, they underwent it themselves. These accounts share a common structure. The outsider approaches the ceremony with a confidence that tends to evaporate very quickly. They receive some briefing on what is about to happen. They put their hand into the glove, and then for the cameras and the community they endure what they can. Most do not complete the full 10 minutes with the composure the Satere Mawe boys maintain. Some pull the glove off before the time is done. Some cry out. Some sink to the ground. Most describe afterward that no briefing or mental preparation came close to matching the reality. What is striking about these accounts is not the failure. It is the honesty of the reckoning that follows. The outsiders who speak most clearly about the experience tend to say the same thing, that the pain was beyond what they could have imagined, and that watching the Satere Mawe boys complete the same ordeal across 10 minutes, dancing changed how they understood what a human being is capable of. The cameras capture the pain, but what they capture best is the moment of genuine humility that arrives after it. When the glove is off, when the shaking starts, when the outsider looks across the clearing at the boys who just did what they could not, and finds in that moment that they have no words left for what they are seeing. Among the outsiders who underwent the Tukandera ceremony on camera, 2 in particular became well known to international audiences. Hamish Blake, the Australian comedian and television presenter, wore the gloves as part of a challenge series, and documented the experience with the specific kind of humor that tends to emerge from genuine, uncontrolled pain. His physical response, the trembling, the involuntary sounds, the desperate effort to maintain some dignity was widely shared and watched. He described the sensation as unlike anything he had previously encountered. Steve Backshall, the British naturalist and wildlife television presenter, underwent the ceremony with a different frame of reference. Having spent years working with venomous and dangerous animals, Backshall brought a scientific and experiential background to the ritual that most outsiders lack. His account is detailed, measured, and still emphatic. Whatever preparation his background offered, he reported it was not sufficient. Both accounts, watched by millions of people who will never set foot in the Brazilian Amazon, did something the academic literature on the Satere Maui could not do quite so efficiently. They made the reality of the ceremony visceral and immediate for audiences far from the rainforest. They also drew significant attention to the Satere Maui people themselves, their culture, their territory, and the pressures they face. Anthropologists and indigenous rights researchers have noted that this kind of outside attention is a double-edged thing. It can bring support and protection to a community under pressure. It can also distort, commercialize, and reduce a living tradition to its most visually striking moment. The glove on film is only a fraction of what the ceremony actually is. The Tucandera ceremony of the Satere Maui survives into the present day, but it survives in a landscape that has changed considerably around it. The Satere Maui territory along the Andara and Marau rivers holds legal protections that many other indigenous areas in the Amazon do not have. But legal protection and practical safety are not the same thing. Within the community, the ritual continues to be performed. Boys continue to undergo the ceremony. Elders continue to oversee it. The gloves are still woven from forest materials. The ants are still gathered by those who know how. But the context has changed. Some Satere Maui communities now live closer to cities. Some young people move between the village and the urban world of Manaus and other Brazilian cities, carrying both realities inside them at once. The ritual still happens. Whether it carries the same depth of cultural meaning in communities whose relationship with the forest has been fundamentally altered, that is a question anthropologists and the Satere Maui themselves are sitting with. There is also the growing reality of cultural tourism. Groups of outsiders sometimes travel to observe or participate in the ceremony. The Satere Maui must navigate what it means to share something sacred with people who experience it as spectacle, and how to do that without losing the core of what the ritual actually is. Researchers still debate whether outside observation strengthens or weakens a living tradition over time. For the Satere Maui, that debate is not theoretical. It is the daily texture of a culture trying to remain itself. Every living tradition faces the same fundamental threat in the modern world: time, change, the slow erosion of context that gives a tradition its meaning. For the Satere Maui Tucandera, the threats are specific and identifiable. The first is the loss of the older generations who carry the fullest understanding of the ritual's purpose. When a Peye dies without transmitting the botanical knowledge needed to prepare the ants, something specific and irreplaceable goes with him. When the elders who hold the deeper ceremonial meaning of each element of the ritual are gone, what remains may keep its form but lose its root. The second threat is the pull of the city. Young Satere Maui, people who grow up between the village and the urban world, face choices their grandparents never faced. Each generation that moves further from the forest moves further too from the knowledge the forest holds. The third threat is attention itself. Well-meaning attention, the documentaries, the visitors, the academic papers, can over time reshape a tradition from the inside by changing how its practitioners relate to it. A ceremony performed partly for cameras is not the same as a ceremony performed entirely for the community. Even the shift in gaze changes the light. These pressures are not unique to the Satere Maui. They are the condition of every small culture in the contemporary world. What is unique is the specific thing that may be lost: a relationship with a creature, and with pain, and with what pain can teach a community about itself that nothing in the modern world has found a way to replace. The bullet ant at the center of this endures. The tradition around it is less certain. The Tukandera ceremony asks a great deal. It asks a boy to walk into known pain. It asks him to stay inside it, moving for 10 minutes. It asks him to do this not once, but 20 times across the years of his young life. It asks his family to watch without intervening. It asks his community to witness in silence something they cannot soften. In return, it gives something that is hard to name in the vocabulary of the modern world. It gives knowledge, not intellectual knowledge, but bodily, cellular, permanent knowledge of what a person can endure. It gives the community a shared memory of having seen what each of its members is made of. It gives the young person a self-understanding that was not available before the glove. And it gives, perhaps most crucially, a relationship with suffering that does not require suffering to be avoided at all costs in order for life to be good. Most of us will never stand in that circle. Most of us will never feel what it costs to wear the glove once, let alone 20 times. But the question the ritual asks, what can a person face and who are they on the other side of having faced it, is not a question that belongs only to the Satere Mawe. It is one of the oldest questions a human life can ask. The Tukandera ceremony is one culture's answer, specific, ancient, built from the materials the forest provides. That there are things about a person, deep, true things, that only the hardest experiences bring forward into the light. The bullet ant is not a new animal. Its lineage extends so far back into geological time that the rainforests it inhabits today would not have been recognizable to its earliest ancestors. The most current estimates drawn from molecular clock analyses and fossil comparisons place the emergence of Paraponera and its closest relatives at somewhere between 50 and 60 million years ago, perhaps further. The uncertainty is genuine soft-bodied insects do not fossilize easily, and the bullet ant's full evolutionary backstory is still being assembled from incomplete pieces. 50 million years ago, the Earth was in the Eocene epoch. The continents had largely taken their modern positions, but the world was warmer, the poles were ice-free, and the forests that covered tropical South America were quite different in composition from the Amazon as we know it today. Many of the tree species that modern bullet ants call home, the kapok, the Brazil nut, the Cecropia, had not yet evolved in the forms they currently hold. The bullet ant's ancestors were climbing the trunks of different trees, hunting different prey, living in a rainforest that no human being ever saw. To sit with that span of time, to really let it in, requires the kind of imagination we more often bring to astronomy than to entomology. 50 million years is not history. It is geology. It is the time it takes for ocean floors to migrate, for mountain ranges to rise from sea level, for entire species to appear and vanish from the record entirely. The bullet ant has been here for all of it. The trees around it are younger, the rivers have changed course. The bullet ant, more or less, has stayed. The fossil record of ants is in some respects remarkably good. Insects trapped in tree resin, the ancient substance that eventually hardens into amber, can be preserved in extraordinary detail. Under a microscope, amber-preserved ants from tens of millions of years ago show mandible structure, body hair, even the fine texture of the exoskeleton, almost as clearly as a specimen collected last week. The fossil record of bullet ant ancestors is thinner than researchers would like. The genus Paraponera is known from living specimens and from molecular data, but direct fossil evidence for the bullet ant's lineage specifically is fragmentary. Several candidate fossils from Eocene amber deposits have been proposed as relatives of Paraponera, but identification at the genus level in ancient specimens is difficult, and scientists still debate which ancient forms are true ancestors and which are merely cousins in an old and branching family. What the amber record does show clearly is that the broad category of large primitive ants, to which the bullet ant belongs, was already present and widespread in tropical forests during the Eocene epoch. The specific shape of the animal has been refined over those millions of years, but the fundamental design, the large armored body, the powerful mandibles, the stinger, appears to be ancient. To picture the patience of deep time in a different frame, imagine every human generation that has ever lived, a line of ancestors stretching back through the last several 100,000 years. Now imagine the bullet ant's lineage stretching back 200 times further than that entire line. Not hundreds of thousands of years, tens of millions. The amber it may one day be found in is still resin dripping from a tree somewhere in a forest that no longer exists. A rainforest is not just a collection of plants. It is a network of relationships between producers and consumers, between prey and predator, between species that depend on one another in ways that took millions of years to develop and can unravel in a season. The bullet ant holds a specific place in this network. As a predator, it keeps populations of other insects in check. Beetles, katydids, caterpillars, spiders, the animals that bullet ants hunt on a nightly basis, are also the animals that, left unchecked, could strip leaves, damage bark, and destabilize the food supply of other species further along the chain. This kind of top-down regulation is not unique to bullet ants. Many predators perform the same service in their ecosystems, but the bullet ant performs it with unusual consistency. Its small, stable colony size means it does not strip entire prey populations the way army ants can. Its solitary foraging means it works quietly and individually, taking from the forest only what a single worker can carry. Its long lifespan means it continues this work across years and decades, without pause, without surge. Ecologists studying the role of large predatory ants in neotropical forest ecosystems have described the bullet ant as something like a slow, constant river, not the most dramatic force in the forest, but the one that over time shapes the stone most deeply, persistent in a way that occasional floods are not. The forest around a bullet ant colony is subtly but measurably different from the forest where no bullet ant lives. More leaves remain. Certain prey populations are held at levels that allow the whole system to breathe. The ant does not know this. It is simply hunting. But the forest knows. The bullet ant does not think of itself as a pollinator. It has no interest in flowers. It is not visiting blossoms out of any ecological duty. It is climbing through the canopy at night in search of nectar and prey, doing what it has always done. And yet, inadvertently, invisibly, without any intention, it carries pollen. The extrafloral nectaries that bullet ants visit are often located near flowers or fruiting structures. As the ant moves from nectary to nectary across leaves and branches and bark, it picks up and deposits the pollen of plants along its path. The amounts involved are small. The effect is difficult to measure precisely. Researchers studying the nocturnal ecology of bullet ant foraging have suggested that this incidental pollination may benefit certain plant species, particularly those with night-active flowers positioned along the routes that bullet ant foragers habitually travel. Whether this constitutes true pollination in any meaningful ecological sense or merely a negligible transfer of genetic material, scientists have not fully resolved. The studies are few, and the methodology for measuring the contribution of a single solitary forager moving through a complex canopy at night is genuinely difficult. What is clear is that the bullet ant in its long nightly travels is not simply taking from the forest. It is part of the movement of material through the system. Nectar comes in, pollen goes somewhere else. Prey disappears from one place and reappears as nutrition for a colony deep in the roots. The forest runs in part on exchanges so small and so slow that no single eye can see them. The bullet ant is one of those exchanges, moving in the dark through a system that depends on its passage. In the science of conservation biology, there is a category of species called indicator species. These are animals or plants whose presence or absence tells researchers something accurate and specific about the health of the ecosystem around them. Certain fish indicate water quality. Particular birds indicate old-growth forest structure. Lichen indicates air purity. Each indicator is a living measurement, reading the landscape in a way that no instrument can quite replicate. The bullet ant is becoming recognized as one of the more reliable indicators of intact primary rainforest in the neotropics. The reason is straightforward. Bullet ants require specific conditions that only old-growth forest provides. Large buttress-rooted trees, dense, stable canopy, high, consistent humidity, a diverse prey base, and a rich supply of extrafloral nectaries from long-established trees. Younger, regenerating forests, even those that look lush and green to a casual eye, often lack one or more of these elements. A forest survey that finds bullet ants is by implication a survey of a forest still doing most of what a primary forest should do. A survey that does not find them in an area where they should be present suggests that something fundamental has shifted even if the trees still stand and the leaves are still green. You do not need to examine soil chemistry or conduct aerial surveys. You can walk the trails at dusk, listen for the soft chirp in the leaf litter, look at the base of the oldest trees. If the bullet ant is there, the forest is there. If it is not, something has been lost, not just the ant, but the web of conditions that allowed it to exist. The ant, in this sense, is still speaking for the forest, as it has been perhaps since before the forest had a name. The Amazon rainforest is the largest tropical rainforest on Earth. It is also one of the most rapidly disappearing. In the decades since the 1970s, tens of millions of hectares of Amazon forest have been cleared for cattle ranching, soy agriculture, logging, and infrastructure development. The rates have fluctuated with government policy and international pressure, but the overall trend across half a century has been loss. Significant compounding in many places, irreversible. The bullet ant does not survive in cleared land. It does not adapt to pasture or soy fields or logging roads. It needs the deep forest. And the deep forest is retreating. The species is not on any endangered list. Its overall range remains large enough that the total population has not collapsed to crisis levels. But within that still large range, the habitat is fragmenting. The large continuous blocks of primary forest that allow healthy, stable bullet ant colonies to persist are becoming smaller islands, surrounded by cleared land the ant cannot cross. Scientists studying the long-term effects of habitat fragmentation on ant communities in the Amazon have found that the first species to disappear from forest fragments are typically the large, slow-reproducing, territory-dependent ones. The bullet ant fits that profile precisely. Not the first to arrive in a disturbed landscape, but among the first to quietly vanish from it. There is an irony here that the forest floor does not comment on. One of the most feared creatures in the rainforest, one of the longest-lived, most chemically formidable, most ancient insects on Earth, quietly vulnerable to a chainsaw. Range, loss, and habitat fragmentation are not the same thing, and the distinction matters for a species like the bullet ant. Losing range means losing the total area where a species can be found. Fragmentation means that the remaining range is cut into smaller and smaller pieces, separated by land the species cannot cross. The bullet ant is experiencing both simultaneously. A bullet ant colony occupies one location for decades. It does not pick up and move when the forest around it changes. If the trees are cleared, the colony dies in place. And because bullet ant colonies are small, a few hundred individuals reproducing slowly, establishing new colonies rarely. There is no reservoir of animals waiting to repopulate cleared areas when conditions eventually improve. The gap between two forest fragments might be only a few hundred meters of open land. For a leafcutter ant or a fire ant, that gap can be crossed. For a bullet ant, which walks slowly alone, and whose new queens are highly vulnerable in open, exposed ground, even a modest clearing can be an uncrossable boundary. What this means in practical terms is that the genetic diversity of bullet ant populations is likely declining. Colonies that once exchanged new queens with other colonies a kilometer or two away are now isolated. The small populations become smaller. The pool of genetic variation, the raw material of adaptation, and long-term resilience narrows with every generation. To picture the long-term consequences, imagine a community living on an island that is slowly, imperceptibly shrinking. Not dramatically. A meter at the edges per generation. No crisis visible in any single year. But the island gets smaller, and the people on it, having nowhere else to go, grow fewer. The bullet ant is a creature of humidity. Its nest depends on consistently moist soil. Its foraging depends on a canopy that stays green and productive across the year. Its eggs, larvae, and pupae require the stable temperature and moisture conditions that only a healthy, intact rainforest floor provides. Climate change is making the Amazon drier. The relationship between deforestation and precipitation in the Amazon is well established. Trees release vast amounts of water vapor into the atmosphere through transpiration. That vapor forms clouds which produce rainfall, which keeps the forest wet, which allows more trees to grow, which releases more vapor. The Amazon generates a significant portion of its own rainfall through this cycle. Remove enough trees and the cycle begins to break. Less transpiration means less cloud formation. Less rainfall means drier conditions. Drier conditions stress the remaining trees, reducing their capacity to transpire, reducing rainfall further. The relationship works the way a single tree in a garden works. Cut it down, and the soil underneath dries within a season. The shade plants wilt. The rain stops pooling. Now imagine that process at the scale of a continent. Scientists studying this feedback loop have described a tipping point, a level of forest loss beyond which the Amazon may shift, not gradually but relatively quickly, toward a drier, more open ecosystem. Scientists still debate exactly where that tipping point lies and whether it has already been crossed in some regions. The bullet ant evolved over tens of millions of years, for the deep wet forest has no adaptation for a drying Amazon. It cannot migrate to wetter ground if the forest becomes seasonal scrubland. It cannot wait out a years-long drought. It simply waits in its humid nest for a forest that may not always be there to wait in. The same molecule that has made the bullet ant one of the most feared insects on Earth has also made it one of the most scientifically interesting. Ponerotoxin's ability to produce extreme, specific, prolonged pain by targeting sodium channels in nerve cells has drawn the attention of pain researchers for decades. Pain is one of the most complex and least well understood areas of human medicine. The mechanisms by which nerves transmit pain signals and the ways those signals can be modulated or blocked are still being mapped with care and difficulty. A molecule that activates pain pathways as precisely and powerfully as ponerotoxin is, from a research perspective, a remarkable tool. It allows scientists to study the specific nerve pathways involved in chronic and acute pain with a degree of clarity that other compounds cannot provide. By understanding exactly how ponerotoxin binds to and holds open sodium channels, researchers can better understand the underlying architecture of pain itself, where it lives in the nerve, how it travels, and where it might be interrupted. Most of us will never be stung by a bullet ant, but the molecule it carries may one day reach us anyway, refined, reworked, transformed by chemistry into something that quietly reduces the pain of a chronic illness, a nerve condition, a slow bodily suffering that a doctor has struggled for years to address. That possibility is still distant and uncertain, but the research is active, and the question being asked in laboratories far from the Amazon by scientists who have never walked a rainforest trail at dusk is one of striking, almost poetic irony. Can the molecule that creates the worst pain in the world also be used to end pain? The search for new painkillers is one of the most urgent problems in modern medicine. The drugs currently available, opioids, anti-inflammatories, nerve blockers, are effective but imperfect. Opioids carry the well-documented risks of dependence and overdose. Anti-inflammatories carry long-term risks to the heart and digestive system. For patients with severe chronic pain, the options are too often inadequate, and the side effects can be as debilitating as the pain itself. Ponerotoxin has attracted scientific interest because of where it works in the pain system. It targets sodium channels with a specificity that many existing drugs do not match. If researchers can understand the mechanism of its binding well enough to design a molecule that works in reverse, blocking the channel rather than locking it open, they would have the blueprint for a painkiller operating through a pathway currently underserved by available medicine. The technical challenges are significant. Ponerotoxin itself, in its natural form, is difficult to synthesize in usable quantities. It is a peptide broken down in the digestive system and unable to be taken as a pill. Delivering it, or a safely modified version of it, to specific nerves without affecting the rest of the nervous system requires engineering that does not yet exist. Scientists still debate whether the therapeutic promise of ponerotoxin-based compounds will ever be fully realized, or whether the molecule's unique properties will prove too difficult to harness safely at scale. But the conversation is happening. In research hospitals and university laboratories, the bullet ant, the creature that gave the world its highest pain score, is being studied as a possible source of relief from the very thing it inflicts. The forest, for all it has lost, is still giving. Ponerotoxin is not a complicated molecule by the standards of organic chemistry. It is a relatively short peptide, a chain of roughly 25 amino acids folded into a specific three-dimensional shape that allows it to interact with sodium channels in nerve membranes. Chemists have mapped its structure in detail. They understand, at least in outline, how it works. And yet synthesizing it in meaningful quantities for research purposes has proven consistently difficult. The challenge is not the molecule itself exactly, it is the folding. A peptide of this kind must be arranged into a precise three-dimensional shape to function. The wrong fold produces a molecule that looks chemically identical but does nothing useful. Producing the right configuration in a laboratory is something like trying to recreate a specific whisper from a written description of its sound. You can know every word without capturing what makes it work. In the living bullet ant, the venom gland produces ponerotoxin with extraordinary precision in exactly the right configuration, in exactly the right quantities. In a laboratory, achieving the same result requires conditions that are expensive, slow, and not always reproducible. Several research groups have produced synthetic ponerotoxin in small quantities, enough to study in cell cultures and animal models, but not enough to advance into the large-scale testing that pharmaceutical development requires. The alternative harvesting ponerotoxin from living bullet ants is both logistically difficult and ethically complicated. The quantities available from a single colony are tiny. The stress placed on the ants during collection is significant. Researchers are investigating whether bacteria, yeast, or engineered cell lines might be induced to produce the peptide at scale. The approach has worked for other complex biological molecules. Whether it will work for ponerotoxin remains for now an open question. The venom of the bullet ant is not a single molecule affair. Ponerotoxin is the primary active ingredient, the headline compound, the one that earned the species its reputation. But venom is by its nature a complex mixture, the product of millions of years of evolutionary refinement, tuned to do specific things to living tissue with great efficiency. And efficiency in biological molecules tends to translate into research opportunity. Bullet ant venom contains, in addition to ponerotoxin, several other bioactive compounds whose functions and potential applications are still being explored. Some appear to have antimicrobial properties, the ability to disrupt or destroy bacteria in ways that could be relevant to the growing problem of antibiotic resistance. Others appear to interact with immune system pathways in ways that researchers do not yet fully understand. The field of venomics, the systematic study of venoms for biomedical applications, has expanded rapidly in recent decades. Cone snail venom has already yielded a painkiller in clinical use. Spider venom has provided compounds being studied for stroke treatment. Wasp venom has produced antimicrobial peptides under active investigation. In each case, the source of the medicine was a creature most people would run from. The bullet ant fits this pattern. The same venom that has made it the most feared insect on Earth also makes it, in the eyes of researchers who study such things, a biochemical library. A small, armored, impeccably maintained archive of compounds that evolution has been perfecting since before the Andes existed. Most of what that archive contains has not yet been read. The research is early, the questions are large, and the library is still open in the roots of the forest waiting. For all that is known about the bullet ant, there is a great deal that is not. Science does not fully understand why bullet ant colonies are so small. The most widely accepted explanations, diet, foraging strategy, nesting constraints, account for some of the pattern but not all of it. Colonies of other large, primitively organized ants can reach sizes many times greater than those of bullet ants under similar conditions. Something specific to the bullet ant's biology appears to limit population growth, but what that something is remains unclear. Science does not fully understand how bullet ants navigate. Solitary foragers in complex environments typically use landmark memory, dead reckoning, and chemical trails to find their way. Bullet ants use the first two, but their trail marking is minimal. The exact mechanisms by which a lone bullet ant finds its way back to a nest it left hours ago in the dark, across a forest floor that may have shifted with rain, and fallen leaves are not completely mapped. Most of us have encountered at some point the specific feeling of knowing something in the body that we could not find words for. A familiarity with a place, a sense of direction in an unfamiliar city that turned out to be correct. The bullet ant navigates its forest through something like this. Whether to call it knowledge or instinct, or something for which no adequate word yet exists that is the kind of question that depends on what we decide the words mean. These are not questions science is close to answering. Some of them may never be answered at all. Of all the behaviors that make the bullet ant unusual among ants, the solitary foraging habit is perhaps the most mysterious. It runs so counter to the fundamental logic of ant sociality, the logic that says the colony is the organism and the individual is just a part of the whole, that explaining its emergence requires genuine thought. The leading hypothesis among researchers who study the evolution of ant foraging systems is that solitary foraging in the bullet ant is a consequence of its large body size, combined with a diet that is both scattered and diverse. A large ant can capture and carry prey that smaller ants cannot tackle. But the same prey items, individual beetles, spiders, large caterpillars, tend to be distributed through the forest in unpredictable low-density patterns. They do not cluster in a way that rewards the kind of trail-following mass recruitment behavior that leafcutter ants use for their predictable leaf sources. If the food is scattered and unpredictable, a single searching forager may locate it more efficiently than a coordinated column of workers following a fixed route. The trade-off is that information about the food source is not shared, but in a landscape where each find is unique and unlikely to be in the same place twice, sharing may have limited value. This hypothesis is elegant but not proven. It fits the available data without fully explaining why certain bullet ant relatives with similar body sizes and similar diets have in some cases evolved different foraging strategies. Scientists still consider the question open. The answer, when it comes, may tell us something fundamental about the relationship between body size, diet, and the evolution of cooperation itself. The bullet ant has no conservation plan written specifically for it. There is no international treaty protecting its range. There is no captive breeding program, no species recovery team, no dedicated monitoring effort tracking colony density across the Amazon basin. What exists instead is a patchwork of indirect protections. Indigenous territory designations that protect the forests some bullet ant populations live in. National park boundaries that have in places preserved primary forest that might otherwise have been cleared. Research programs focused on the broader health of Amazon ecosystems that include the bullet ant, incidentally. In their monitoring, this patchwork is imperfect. Indigenous territories are under constant pressure from illegal logging, mining, and encroachment. National park boundaries are porous in practice. Research programs are underfunded, and their continuity depends on grant cycles shaped by priorities other than the slow reproducing armor-plated inhabitants of the forest floor. The bullet ant survives for now, not because anyone has decided to save it, but because enough of its habitat has survived for other reasons. The rainforest that protects it is the same rainforest that holds the water supplies, the carbon stores, and the biodiversity that human civilization increasingly recognizes it cannot afford to lose. The bullet ant is, in this sense, a passenger in someone else's conservation story. The effort being made is for the forest, the climate, the rivers, and the thousands of other species that share the same threatened ground. But the bullet ant benefits. Quietly. Not by asking for anything, but by being old enough and fierce enough and patient enough to still be there. Before any conservation biologist walked the forests of the Amazon with a clipboard and a research grant, the bullet ant had protectors. They did not call themselves conservationists. They called themselves in their various languages the people of the forest, and their knowledge of the ant, accumulated across hundreds of generations of living alongside it, constitutes one of the most detailed and durable bodies of understanding the species has ever had. Indigenous peoples of the Amazon have long understood without formal ecological training that the bullet ant is a marker of forest health. They know which trees the ant prefers. They know its seasonal patterns. They know the sounds it makes and what those sounds mean. They know how to approach a colony without triggering mass defense, and how to harvest worker ants for ceremony without destroying the colony itself. The relationship between this indigenous knowledge and the formal science that studies bullet ants is in some sense like the relationship between a long-practiced craft and a recently published textbook about the same subject. Textbook may be more systematic, but the craft often knows things the textbook has not yet thought to ask about. Researchers have increasingly recognized what they were missing by working without it. Ethnobiologists and conservation scientists have begun carefully and with the consent of communities to learn from the ecological knowledge that indigenous people carry. This knowledge is not written down in any scientific journal. It is transmitted orally in ceremony and practice, in the quiet teaching that happens when an elder walks beside a younger person through the forest and stops at the base of a particular tree. The bullet ant has had many observers across its long history. The longest tenured, and perhaps the most attentive, have been the people who never stopped living beside it. The bullet ant entered the formal record of European science through the door that most tropical organisms had to pass through in the 17th, 18th, and 19th centuries. The journals and specimen cabinets of natural historians who sailed to the tropics and returned with boxes of dried insects and handwritten notes. One of the earliest formal scientific descriptions of the species was produced by the Danish naturalist Johann Christian Fabricius in the late 18th century. Fabricius, working from preserved specimens rather than living animals, gave the ant one of its early Latin names and placed it within the taxonomic systems of the day. His description was clinical accurate in its physical details, and entirely silent on the matter of the sting, which is one of the inevitable consequences of working from a dead specimen. You can measure an ant. You cannot feel what it did when it was alive. Later, naturalists who encountered the species in the field added what Fabricius could not: the behavior, the sound, the pain, the accounts of ants standing their ground against animals many times their size. These field-based descriptions, accumulated across the 19th century, gradually built the portrait that science now holds. What is striking about reading the oldest accounts is how little the essential facts have changed. The size, the color, the habitat, the chirp, the sting, all described in the 19th century in terms a modern entomologist would recognize without difficulty. The bullet ant encountered by European science for the first time was already fully itself, already ancient, already carrying everything it carries now. The scientists were new to it. The ant was not new to anything. The insect world contains extremes that challenge the imagination. The strongest animal on Earth, measured by body weight, is a dung beetle. The fastest insect is a dragonfly. The longest lived is a queen termite surviving for decades in her sealed chamber. The most complex society belongs perhaps to the honeybee. The most painful sting belongs to the bullet ant. It is an unusual record to hold. In almost any other category, size, speed, colony population, reproductive rate, the bullet ant is unremarkable. It is a mid-sized ant, slow-moving by insect standards, with a small colony and a modest reproduction rate. It does not build anything architecturally remarkable. It does not migrate in swarms. It does not change color or glow, or produce silk, or perform any of the dozens of other remarkable things that different insect species have evolved to do. What it has is the venom. And the venom is enough. In a world of millions of insect species, each one a small marvel of evolutionary engineering, the bullet ant holds a single, very specific distinction. Not the broadest, not the most complex, not the most numerous, just the most painful. There is something almost monastic about it, a creature that has given up diversification and expansion and spectacle in favor of one thing done to a degree that nothing else in nature has matched. A specialist in an extreme, a small, dark, unhurried figure carrying the worst chemistry in the insect world through a shrinking forest at night in silence, asking nothing, yielding nothing. There is a peculiar honesty required when studying a creature as old as the bullet ant. The admission that science, for all its tools and methods and accumulated knowledge, has not finished with this small insect, has not finished and may not finish in any lifetime currently running. The deepest questions about the bullet ant are not the ones that better microscopes or more sophisticated genetic analysis will answer. They are the questions that touch on the nature of animal experience, on what it is like, if it is like anything, to be a creature that has lived in essentially the same form for 50 million years. Does the bullet ant experience the chemistry of the forest around it as something like pleasure? Does the colony have at any level something that could be called an awareness of itself as a whole? Does a lone forager returning in the dark to its nest feel anything that resembles relief? These are not questions that any current scientific framework can answer with confidence. The field of animal consciousness is one of the most contested areas in all of biology, and invertebrate consciousness is its furthest and most uncertain frontier. Researchers still debate whether insects have anything resembling subjective experience at all, or whether the question itself is meaninglessly applied to a nervous system so unlike our own. And yet, the bullet ant walks. It learns routes through a complex forest. It finds its way home in the dark. It has been doing this without pause since before our species stood upright. What it knows of the world, in whatever sense knowing is available to it, is something we have not yet found the right question to ask about. At the end of everything, the bullet ant walks back into the dark, not as a metaphor, not as a conclusion, literally as it does every night when the light fades and the ant leaves its nest and climbs the trunk of its tree and enters the canopy and begins the slow, patient work it has been doing since long before the first human being stood upright on the savannah and looked at the sky. We have spent this time together learning what the bullet ant is, the length of it, the sound of it, the chemistry of its venom and the architecture of its nest and the ceremony built around its sting by people who have lived beside it since before the word civilization existed. We have followed its lineage back to the Eocene epoch and followed its venom forward into the research laboratories of today. And at the end of all of that, what the bullet ant remains is what it has always been. A small, dark, armored creature walking alone through the roots of the forest, carrying inside its body a molecule that has no equivalent anywhere else on Earth. It does not know it has been studied. It does not know its name in Latin or in English or in the other languages that have found a word for it. It does not know that somewhere on a screen in a room far from the rainforest a person is learning about it tonight for the first time. It knows the bark beneath its feet. It knows the chemical signature of its sisters. It knows the darkness ahead and the nest behind, and the particular texture of a single night in a forest that has been giving and taking life across a span of time that makes the whole of recorded human history look like a single afternoon. We are not the oldest things on this planet. We are not the most patient. We are not the ones who have been here long enough to see the deep shape of things. The bullet ant has been here. It is still here. It will be here long after this night is over, climbing in the dark through a forest it has known longer than we have had a word for any of it. And if the forest survives, so will the ant. Small and unhurried and carrying everything.